Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route toward rest. Tonight's story begins far away from the ticking of clocks or the glow of the room you're sitting in. We're going to drift gently into the very centre of our galaxy, a place most of us will never see, but which shapes the Milky Way itself. At the core of that immense spiral lies something so strange, so powerful, and yet so quiet that for most of human history, we didn't even realise it was there. A supermassive black hole known as Sagittarius A, the hidden heart of our galaxy, the monster that devours, shapes, and guides the Milky Way. Before we ease into that mystery, though, let me ask you something simple. Where are you listening from tonight? Are you tucked into bed, perhaps with the soft hum of a fan nearby, or maybe resting on the couch after a long day, phone in hand, light dimmed? Is it late evening where you are, or early morning, or maybe the middle of the night when the world feels quiet enough to think about distant stars? It's funny, isn't it? How we can share this moment while being scattered across time zones, each of us with our own view of the night sky, yet all of us orbiting together around that same galactic centre. If you find this little journey calming, if it helps you feel soothed or sparks your sense of wonder, while also letting your body unwind, I'd be grateful if you gave the video a like or subscribe. It helps this quiet corner of the internet reach others who might also enjoy a peaceful way to drift into sleep while still learning something marvellous. So now, let's settle in, slow your thoughts, soften your breathing, and imagine with me. Somewhere, 26,000 light years from where you lie right now, hidden behind clouds of dust and stars, sits a region of space that is at once invisible and undeniable. It's neither a star nor a planet nor a nebula. It is a gravitational well so strong that nothing, not even light, can escape it. And yet, curiously, its existence was not obvious to us until very recently in human history. For centuries, our species gazed at the night sky, naming constellations, charting paths, and spinning stories about archers, gods, and hunters. The constellation Sagittarius, the archer, was drawn by cultures across the globe, its bow pulled tight against the backdrop of the Milky Way. But no one suspected that hidden in that hazy patch of sky, at the place where the archer's aim points, was something no myth had ever quite imagined. The name Sagittarius A doesn't sound very romantic, does it? It's a product of radio astronomy cataloguing, a label given when scientists began mapping strange signals coming from deep space. The A is just part of a classification system, one among many radio sources in the Sagittarius constellation. But this unassuming letter hides an extraordinary reality. What it points to is not just a source of radio waves, but the very heart of our galaxy, a black hole 4 million times the mass of our Sun. When we speak of it as a monster devouring our galaxy, it's tempting to picture something loud and obvious, like a cosmic predator gobbling stars. But Sagittarius A doesn't roar across the sky. Instead, it waits silently, patient, its influence invisible except for the way nearby stars are compelled into tight, dizzying orbits. In that sense, it's more like a hidden engine, a gravitational anchor around which the entire Milky Way is balanced. Without it, the galaxy we call home would not look the way it does. Think for a moment about where you sit right now. The chair, the bed, the floor beneath you. All of it rests on Earth, a planet circling a star, which itself lies halfway out on one of the Milky Way's spiral arms. And all of those stars, hundreds of billions of them, are held in a dance orchestrated by that unseen presence at the centre. You are connected by the pull of gravity to Sagittarius A, whether you ever thought about it before tonight or not. When astronomers first began to suspect that something massive lurked at the centre of the Milky Way, the idea of black holes was still controversial. Einstein's theory of general relativity had predicted them as possible solutions to his equations, but even Einstein himself doubted whether nature would allow such exotic objects to exist. For decades, black holes were a mathematical curiosity, like something sketched in the margins of physics rather than an accepted part of the cosmos. And yet, as technology improved, we kept stumbling across hints, strange motions of stars, odd sources of radiation, energies too intense to explain by ordinary means. It took time to piece the puzzle together, but Sagittarius A eventually revealed itself not in sight, but in motion. Stars near the galactic centre whip around invisible points at incredible speeds, some completing orbits in mere years despite being many times farther from the centre than our own solar system is wide. The only explanation for such violent accelerations was something compact, enormously heavy, and yet hidden from view. A supermassive black hole, right there, at the crossroads of our galaxy. If you let your mind drift with that thought, there's something both humbling and oddly comforting about it. At the centre of our shared home lies a mystery so deep it swallows light itself. And still, here we are, billions of years later, circling safely, telling stories, listening and learning. That silent giant is not rushing toward us, nor plotting our end. It simply exists, immense and steady, anchoring the spiral arms, shaping the Milky Way's history, and reminding us how much lies beyond our little patch of sky. What we'll do tonight is slowly walk around this subject in no hurry, as if we were circling a dark lake and peering gently into its depths. We'll talk about what Sagittarius A is, how it was discovered, how it behaves, and what it means for our understanding of the universe. We'll look at the strange orbits of stars, the way matter glows as it spirals inward, the faint radio whispers that reach us across light years, and the astonishing feat of taking a picture of something that cannot be seen directly. We'll explore what happens to space and time near its edge, and we'll wonder about the paradox of destruction and creation entwined in its core. And we'll do all of this not quickly, but slowly, as if the very act of stretching these thoughts out helps us settle into rest. Sagittarius A is sometimes called the monster at the heart of our galaxy. And while that phrase can sound frightening, it is worth remembering that monsters too are part of stories. This one is not a creature lurking with malice. It is gravity itself, drawn into a shape that challenges our imagination. It doesn't hunt, it doesn't chase, it waits as the galaxy turns around it. And perhaps there's something peaceful in that image, something steady in knowing that the same immense presence has been there since long before Earth even formed, and will be there long after. So, as you lie back and let your eyelids grow heavy, think of yourself as part of a spiral that stretches across 100,000 light years, all of it gently tethered to a dark heart. A heart we cannot see directly, but which we can trace in the movements of stars and the glow of matter as it disappears. A heart called Sagittarius A. And from here, we'll take our first step deeper, easing into how this hidden core first revealed itself to curious eyes scanning the sky. If you step outside on a clear night far from city lights, and you let your eyes adjust to the darkness, you'll notice a pale, misty band stretching across the sky. That band is the Milky Way, our home galaxy seen from the inside. To the human eye, it looks like a soft river of stars, a glowing cloud painted across the heavens. Ancient cultures told stories about this band, calling it the path of souls, the spilled milk of gods, the backbone of the night. Long before we had telescopes or radio dishes, people knew instinctively that this was something greater than the single stars scattered elsewhere in the sky. It was denser, richer, more mysterious. What none of them could have guessed was that buried deep in the brightest, most crowded region of that glowing band lies a secret that would take modern science centuries to uncover. The central bulge of the Milky Way is not a place the eye can easily see. From Earth, we're positioned about halfway out along one of the galaxy's spiral arms, some 26,000 light-years from the middle. Between us and the core lies a thick curtain of dust and gas that blocks visible light. That's why if you point a regular telescope at the centre of the galaxy, you won't see much beyond a hazy glow. The The visible universe hides what's happening there. But other forms of light, infrared, radio, X-rays, can pierce that curtain, and when astronomers began using those tools, the picture that emerged was stranger than anyone had imagined. The hidden heart of the Milky Way is a place of extremes. Stars are packed thousands of times more densely than they are in our neighbourhood of space. Clouds of gas swirl under immense gravitational forces. Radiation flashes and flares unpredictably. It is a bustling, chaotic region, and right at the centre sits Sagittarius A, the supermassive black hole. To reach it, you would have to pass through environments so unlike our calm solar system that they feel almost like another universe. Here, a single cubic light-year might contain hundreds of stars. Here, gravitational tides stretch and warp everything that drifts too close. For most of history, though, all of this was hidden. The earliest telescopes showed the Milky Way's central bulge as a glowing concentration of starlight, but it was only in the 20th century that astronomers began to realise something more was happening there. When radio astronomy blossomed in the mid-1900s, scientists detected powerful signals coming from the constellation Sagittarius. They called the source Sagittarius A. At first, it was just one among many strange radio sources catalogued across the sky. But this one was different. It was steady, central, and stubbornly bright. It didn't match a typical star, nor a nebula, nor a supernova remnant. Something unusual lived there. The hidden heart was slowly revealing itself. As instruments improved, astronomers turned to infrared observations. Unlike visible light, infrared can slip through the dust that clogs the galactic centre. When they peered at the region this way, they saw stars darting around as if whipped by an invisible leash. Some of these stars moved at thousands of kilometers per second, racing through space on elongated paths that betrayed the presence of an unseen mass pulling on them. Imagine watching leaves on a pond, spinning and swirling around a spot where no stone or log can be seen. The only explanation is that something heavy, hidden beneath the surface, is dragging them. In the galactic centre, that hidden weight was a black hole. It is difficult to grasp the scale of this hidden heart. The Milky Way as a whole is vast, roughly 100,000 light-years across, with perhaps 400 billion stars scattered through it. The central bulge, by contrast, is a few thousand light-years wide, but in that smaller space, tens of billions of stars are packed together. At its very centre, all of that activity orbits a single object, Sagittarius A, which holds the mass of 4 million suns inside a region smaller than the orbit of Mercury. That contrast, immense mass, tiny space, is what makes it a black hole. Gravity there is so strong that nothing can escape once it crosses the boundary known as the event horizon. Yet the hidden heart of the Milky Way is not dark in the way you might imagine. Even though the black hole itself is invisible, the material falling toward it heats up and glows. Gas and dust spiral inward, forming what astronomers call an accretion disk, a whirling platter of matter so hot it emits radiation across the spectrum. Sometimes, flares erupt when chunks of gas are swallowed, sending out bursts of X-rays that reach us across light years. To an observer nearby, it would be a place of violent brilliance, like fireworks constantly going off in the night. From our vantage point, the light is dimmed and scattered, but careful instruments can detect it, telling us about the activity around the black hole. This hidden heart is also a place where stars live unusual lives. Some of them, called the S-stars, follow wild, looping orbits that bring them perilously close to Sagittarius A before slinging them back out again. One star in particular, known as S2, completes an orbit in just 16 years, whipping around at speeds of several thousand kilometers per second. By tracking these orbits with exquisite precision, scientists confirm the existence of the black hole. Nothing else could explain such extreme motion. No cluster of smaller objects could survive packed into such a small space without collapsing. Only a supermassive black hole fits the data. When you think of the hidden heart of the Milky Way, it's helpful to imagine layers. The outer spiral arms where we live are like the suburbs, spacious and relatively calm. Close to the centre, the bulge is like a crowded city full of stars and activity, and at the very downtown core, hidden by skyscrapers of dust and gas, is the central engine itself, Sagittarius A. From the suburbs, you can't see the engine directly. You see only the glow of the city lights. But with the right instruments, the heart is unmistakable. It beats with gravity so strong it binds the galaxy together. There's something almost ironic about this hidden heart. It is, in a sense, the most important object in our galaxy, and yet it's invisible to our eyes. We cannot look up and say, there it is. Instead, we infer its presence by the behaviour of everything around it. This is how science often works. The most powerful forces in nature are not always the ones we see directly. They are the ones we detect through influence, through effect, through the way they shape what surrounds them. Gravity itself is like that. We never see gravity. We see falling apples, orbiting moons, circling stars. The hidden heart of the Milky Way is simply gravity made extreme, a concentration so dense it creates a hole in the fabric of space. To sit quietly and think about it is to realize that we are living in a galaxy with a secret. Every night when the Milky Way arches overhead, that secret is glowing softly behind dust and distance. Most people never stop to think about it, yet all of us are part of its story. The black hole at the centre is not just some distant curiosity. It is the anchor of our home, the point around which everything turns. If you could zoom out far enough, if you could see the Milky Way in its entirety, you would notice the spiral arms winding around that hidden heart like dancers around a silent partner. Astronomers often describe the galactic centre as both violent and beautiful. Violent because of the energies unleashed there, the collisions, the flares, the crushing gravity. Beautiful because those same forces give rise to patterns of light, to orbits of elegance, to a kind of cosmic choreography. The hidden heart is not a place we could ever visit safely, but from afar it is a reminder of what lies beneath the surface of ordinary appearances. And perhaps that's why it fits so well into a quiet evening of thought. The idea that beneath the visible, beneath the ordinary, there is always something hidden, something deeper. In the case of our galaxy, it is a heart we cannot see but that holds us all. When we turn our attention from the broad glow of the Milky Way's heart to the specific object that lives there, we encounter something that pushes the limits of imagination. Sagittarius A is the name we've given it, though the name itself feels almost too simple for what it represents. To call it a black hole is already to step into a world where words begin to fail, because a black hole is not really a hole at all. It's not an object in the way we think of stars or planets. It's more like a region of space where gravity has collapsed matter so completely that nothing, not even light, can escape. What we meet at the centre of the galaxy is not a thing you could touch, not a surface you could stand on, but rather an invisible boundary around an unknowable core. And yet, this absence of light, this impossible well, is also a presence that shapes the destiny of everything around it. Sagittarius A is classified as a supermassive black hole, a term astronomers use to distinguish it from the smaller black holes formed when individual stars die. Stellar black holes might be a few times the mass of the Sun. Some grow larger, perhaps dozens of times that mass. But Sagittarius A is in another league entirely. It contains about 4 million solar masses, all compressed into a region smaller than the orbit of Mercury. Imagine every star you can see in the night sky, then multiply that by millions, and then imagine squeezing all of that into a single invisible point. That is the appetite of Sagittarius A. It's tempting, when hearing phrases like, the monster devouring our galaxy, to picture a kind of cosmic mouth endlessly swallowing stars. But the truth is subtler. Sagittarius A is not constantly gobbling everything around it like a hungry beast. In fact, Compared to some black holes in distant galaxies, ours is relatively quiet. Astronomers sometimes call it a sleeping giant because it consumes far less matter than it could. Material does fall toward it. Gas clouds drifting too close, stars brushing the edge of danger, fragments of interstellar debris. But most of the galaxy remains safe in their orbits. The monster image comes not from endless feeding, but from the fact that if Sagittarius A chose to feast, its power would be beyond comprehension. Meeting Sagittarius A, even in thought, is a humbling exercise. The first question that comes up is how such a thing came to be. How does a black hole grow so massive? One idea is that in the early universe, enormous clouds of gas collapsed directly into black holes, seeding the centres of galaxies with giants that grew as matter fell in. Another idea is that smaller black holes merged over time, gradually swelling into the supermassive variety. For Sagittarius A, the details remain uncertain. We know it has been there for billions of years, anchoring the Milky Way since its formation, but its exact origin is hidden by the same forces that make it so mysterious now. What we do know is how it reveals itself. Because even though nothing can escape from inside a black hole, the region around it is full of activity. Matter falling toward the event horizon accelerates, collides, and heats to extreme temperatures. It forms a swirling disk of plasma, called an accretion disk, that glows across the spectrum. Sometimes Sagittarius A flickers with flares when clumps of matter spiral inward and vanish. To astronomers, these flares are like fireworks announcing that the monster has taken another bite. They are brief, lasting minutes or hours, but in that time they can outshine entire stars. One of the strangest things about meeting Sagittarius A through observation is realizing that we don't see the black hole itself. What we see is its influence. We see stars whipping around it on tight orbits, their paths betraying the invisible mass at the center. We see radio waves and X-rays emitted by the superheated material as it falls inward. We see the shadow cast against the glow of surrounding light. But the black hole itself, the region beyond the event horizon, remains hidden. In that sense, meeting it is always indirect, like knowing someone only by the ripples they leave in the world, and yet those ripples are unmistakable. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. It was not a crisp photograph in the ordinary sense, but rather a reconstruction from radio signals gathered by telescopes scattered across the Earth. The result showed a glowing ring of light, distorted by gravity, surrounding a dark shadow. That shadow was not the black hole itself, but the absence created by its event horizon. For the first time, humanity looked at the silhouette of the monster in our own galaxy. It was a moment both thrilling and surreal, the invisible made visible by ingenuity, patience, and collaboration. To put its size in perspective, consider this. If Sagittarius A were placed where our Sun is, its event horizon would stretch beyond the orbit of Mercury, but not as far as Venus. In our solar system, that would mean Earth would orbit safely outside it, though the skies would be very different indeed. Instead of a warm, glowing sun, there would be a dark sphere encircled by a bright, turbulent disk of radiation. Life as we know it could never survive there. But in the vastness of the galaxy, Sagittarius A sits quietly at its post, far enough away that its influence on our little world is mostly indirect, felt through the larger structure of the galaxy rather than through any direct pull, and still, the appetite is real. Every so often, astronomers watch as a star wanders too close. In such cases, the gravity of Sagittarius A can tear the star apart in a process called a tidal disruption event. The star is stretched into a stream of gas, half of it flung outward, the other half spiraling inward to be consumed. From Earth, we can sometimes detect the sudden flare of radiation as this happens. It's a reminder that while the black hole may appear calm most of the time, it is capable of dramatic feasts. The phrase "devouring our galaxy" captures the imagination, but it's not a threat in the immediate sense. Sagittarius A is not sucking the Milky Way into itself. Rather, it is like a campfire at the centre of a circle, quietly burning, occasionally flaring, always present. Over cosmic timescales, it will indeed consume stars, gas and dust, but the galaxy is so vast that this process unfolds slowly, almost lazily, across billions of years. For us here and now, the monster's appetite is more a curiosity than a danger. What's more, its appetite plays a role in shaping the galaxy. When black holes consume matter, they often release energy back into their surroundings in the form of jets or radiation. These outbursts can regulate star formation, heating gas and preventing it from collapsing into new stars, or sometimes triggering bursts of activity in galactic centres. Sagittarius A, even in its relative quietness, has likely influenced the history of the Milky Way, guiding its rhythm of birth and death among the stars. There's an odd paradox in meeting Sagittarius A. On one hand, it is the ultimate destroyer, a place where matter and energy vanish beyond recovery. On the other hand, it is also a creator, shaping galaxies, influencing star formation, driving cosmic evolution. The monster devours, but in devouring it helps build the stage on which stars and planets, and eventually life, appear. Without supermassive black holes, galaxies might not form the way they do. Without galaxies, stars like our Sun might never exist. Without stars, there would be no Earth, no oceans, no listeners lying in bed tonight wondering about distant things. The monster at the heart of the galaxy may be terrifying, but it is also, in a strange sense, responsible for our existence. To sit with this thought is to realise how much the universe defies our categories. We want to label things as good or bad, creator or destroyer, safe or dangerous. Sagittarius A is all of those at once. It is a devourer, but also a shaper. It is hidden, yet central. It is silent, yet loud in its influence. To meet it is to confront the limits of our words and the depth of our curiosity. Astronomers will continue to study Sagittarius A for decades to come, refining measurements, testing theories, seeking to understand not just how it behaves, but what it tells us about the nature of reality. Already the orbits of stars near it are being used to test Einstein's theories with extraordinary precision. Already the flares it emits are teaching us about the physics of extreme gravity. Already the shadow image has given us a new way to think about the boundaries of the invisible. Meeting Sagittarius A is not a single event, but an ongoing relationship between human curiosity and cosmic mystery. For as long as humans have looked up at the night sky, the centre of the Milky Way has been there, glowing faintly as part of the hazy band of stars. Yet for most of history, no one had any idea what was hidden there. Even today, with advanced telescopes and radio arrays, the heart of our galaxy remains one of the most mysterious places we know. Part of that mystery comes from sheer distance. We live on the outer edge of one of the galaxy's spiral arms, about 26,000 light-years away from the core. That's an unimaginably long stretch of space, and even light, moving at the fastest speed in the universe, takes all those years to cross it. When astronomers study the galactic centre, they are not looking at what it is doing right now. They are seeing it as it was 26,000 years ago, because that's how long its light and radio signals have taken to reach us. We are always looking into the past, never the present. Distance alone makes it difficult, but distance is not the only obstacle. Between us and the centre lies a vast curtain of dust and gas. To the human eye, that curtain is opaque. If you aim an ordinary telescope toward the middle of the Milky Way, you see very little detail. The light from countless stars is blocked, scattered, and absorbed by thick clouds. It is like trying to peer through miles of fog. What we know of the galactic centre comes not from visible light, but from other parts of the spectrum. Infrared light, radio waves, and X-rays can slip through the dust. Only when astronomers began using these tools did the hidden activity start to reveal itself. Even then, the signals we receive are faint and tangled. The galactic center is crowded with stars, nebulae, and complex structures. Picking out individual details requires extraordinary precision. Imagine standing at one end of a busy city street at night, with headlights, neon signs, and street lamps all blurring together, and trying to pick out the motion of a single firefly. That is what astronomers face when they study the region around Sagittarius A. There is also the fact that the environment itself is extreme. Gravity near the black hole warps space and time. Radiation from the hot gas swirling inward creates bursts and flares. Magnetic fields twist and knot in unpredictable ways. To make sense of this environment, astronomers must build models that stretch the limits of physics. Every observation raises new questions. Every answer seems to open another layer of mystery. One reason the center of the galaxy is so difficult to study is that it doesn't behave in ways we can easily predict. Some days, Sagittarius A seems relatively quiet, emitting only faint radio signals. Other days, it produces sudden flares in infrared or X-rays, brightening by factors of hundreds before fading again. These events are not regular, and they defy simple explanation. Is it a star grazing too close? A clump of gas being torn apart? Magnetic fields reconnecting violently? Each possibility has evidence, and yet none provide a complete picture. The stars themselves add to the puzzle. The so-called S-stars, which orbit close to the black hole, move in paths so extreme that they seem to defy intuition. Some of them loop around in just a few years, at speeds that stretch our ability to imagine. Watching these stars is like seeing a cosmic dance performed at impossible tempos. Yet even after decades of tracking, we still don't fully understand how such stars got there in the first place. Did they form near the black hole, in conditions that should normally make star formation difficult? Or were they captured and pulled inward from farther away? Each scenario poses challenges, leaving astronomers with partial answers but no final story. Another reason the galactic center remains mysterious is its relative quietness compared to other galaxies. Many galaxies host black holes millions or even billions of times the mass of the Sun. Some of those black holes are active, devouring matter at such a rate that they blaze across the universe as quasars, outshining entire galaxies. Ours, by contrast, is subdued. Sagittarius A is underfed, taking in only small amounts of matter most of the time. Why it is so quiet and whether it has always been that way, a question still under study. There is evidence that in the past, Sagittarius A was far more active, perhaps even releasing jets of energy that shape the Milky Way. If that is true, then we are living in a calmer phase, a temporary pause in the black hole's appetite. But how long that pause lasts, and whether it might flare up again, no one can say with certainty. There are also structures around the galactic center that defy easy classification. Enormous radio bubbles stretch above and below the plane of the galaxy, discovered only recently. They are so vast that they dwarf the Milky Way's disk, yet their origin is still debated. Some scientists think they are relics of a past outburst from Sagittarius A. Others suggest they may come from bursts of star formation near the center. Untangling these possibilities requires piecing together evidence from across the spectrum, comparing X-rays, gamma rays, radio signals, and infrared maps. Each clue adds to the story, but the complete picture remains elusive. The challenge is not just technical, but conceptual. Black holes test the boundaries of our theories. General relativity describes gravity on large scales, and quantum mechanics describes matter and energy on small scales. But uniting the two remains one of the greatest puzzles in physics. The galactic center, where gravity is extreme and matter is compressed to unimaginable densities, is the natural laboratory for such questions. And yet, we can only observe from afar, inferring what happens beyond the event horizon without ever seeing directly. It is like trying to understand the inside of a locked box by watching how it rattles when shaken. Even cultural perspectives add to the mystery. For most of human history, the centre of the galaxy was invisible not just physically but conceptually. Ancient cultures mapped the constellations, but the idea of a black hole was beyond imagination. The thought that the Milky Way had a heart, and that its heart was a gravitational abyss, is a very modern realization. In that sense, part of the mystery is simply how alien it feels to our everyday experience. We live in a world where things have surfaces, where light lets us see, where time feels steady. The galactic centre denies all of those intuitions. There, surfaces vanish, light is trapped, and time itself bends. For astronomers, this combination of distance, obscuration, extremity, and unpredictability makes the galactic centre one of the most challenging and rewarding places to study. Every observation requires clever techniques, arrays of telescopes working together across continents, instruments cooled to near absolute zero, algorithms that stitch together faint signals into coherent images. The effort is enormous, but the payoff is equally profound. Each discovery brings us closer to understanding not just Sagittarius A, but the role such giants play in shaping galaxies, stars, and perhaps even life. To think about why the galactic centre is mysterious is also to reflect on our own perspective. We are tiny creatures on a small planet, looking out with instruments that extend our senses but never erase our limits. The mystery is not a flaw in the universe, it is the natural result of the scale we inhabit. To us, the centre of the galaxy will always be mysterious, because we cannot stand beside it, cannot touch it, cannot see it directly. We can only watch from across light years, piecing together faint clues, and perhaps that is enough. As our tools improve, the mystery deepens rather than vanishes. The first image of Sagittarius A did not answer every question. It raised new ones. The flares we observe do not settle debates, they ignite fresh ones. The orbits of stars confirm the existence of the black hole, but they also hint at subtle effects that could reveal new physics. The mystery is not something to be solved once and for all. It is something we live with, something that continues to draw us back to the centre again and again, with new eyes and new questions. For most of human history, the stars were thought to be eternal and unchanging, pinpricks of light on a perfect dome. The Milky Way itself, stretching across the night sky, was interpreted as a band of light, a path of spirits, a river, or the milk of gods. The idea that at the very centre of that glow, hidden behind dust, there might be something monstrous devouring matter was not even imaginable. And yet, slowly, through decades of careful observation and the invention of new tools, astronomers began to suspect that something unseen, something extraordinarily massive was lurking there. The story begins not with black holes but with radio waves. In the 1930s, an engineer named Karl Jansky was working at Bell Telephone Laboratories, studying static that interfered with long-distance radio communications. To his surprise, some of the hiss he detected seemed to come from the sky itself. By tracking it carefully, he realized it peaked when his antenna was pointed toward the constellation Sagittarius, near the center of the Milky Way. This was the birth of radio astronomy, and it planted the first seeds of curiosity about strange signals coming from the galactic core. At the time, no one was thinking about black holes. The signals were simply noted, catalogued, and set aside. But in the decades that followed, as radio telescopes became more powerful, astronomers mapped the sky and noticed that the galactic centre was a particularly strong source of radio emission. It was given a name in the catalogue, Sagittarius A. At first, it was just another radio source among many, but its position was intriguing. Why would the very centre of our galaxy be glowing in radio waves? The next major clue came with the development of infrared astronomy. Unlike visible light, which is blocked by dust, infrared can pierce through to reveal the stars hidden in the galactic core. When astronomers aimed infrared instruments at Sagittarius A, they discovered a cluster of stars packed closer together than anything seen in our neighbourhood of space. These stars were not drifting lazily the way most stars do. They were racing. Their speeds were extraordinary, thousands of kilometers per second, whipping around some unseen center as if tethered by an invisible leash. For scientists, this was the moment when suspicion sharpened. Stars do not move that fast without reason. The only way they could be racing in such tight orbits was if something unimaginably massive was pulling on them. Yet no star, no cluster, no visible object could be found at the center of their paths. It was like watching leaves swirl around a whirlpool in a river, even though the water's surface looked calm. Something powerful was hiding beneath. Through the 1980s and 1990s, teams of astronomers began tracking these stars more carefully. One group, led by Reinhard Genzel in Germany, and another led by Andrea Ghez in the United States, monitored their orbits year after year with increasingly precise instruments. They discovered that one star in particular, later called S2, followed a long elliptical orbit that carried it dangerously close to the invisible center. Every 16 years, S2 swung in, moving at more than 7,000 kilometers per second, before slingshotting back out again. Nothing but a supermassive black hole could explain such behavior. By calculating the orbit of S2 and others like it, astronomers could weigh the hidden mass at the galactic center. The answer was astonishing: about 4 million times the mass of the Sun, crammed into a region smaller than our solar system. No cluster of stars or exotic configuration could explain that density. It was the smoking gun for a supermassive black hole. But suspicion had started even earlier, in ways that might seem quaint now. In the mid-20th century, astronomers noticed peculiar high-energy phenomena near the galactic center, bursts of radiation that didn't match any ordinary star. Some speculated about compact objects, dense remnants of stellar explosions, but the scale was unclear. When quasars were discovered in distant galaxies, extremely bright objects powered by matter falling into supermassive black holes, some astronomers began to wonder if our galaxy also had such a core, only quieter. The pieces began to fit together. It wasn't just radiation and star orbits that raised suspicion. The very structure of the Milky Way seemed to demand something massive at its heart. Galaxies are held together by gravity, and spiral galaxies like ours appear to be stabilized by central concentrations of mass. Theorists began to argue that supermassive black holes were not rare accidents, but natural features of galaxy formation. If other galaxies had them, why not ours? The idea that the Milky Way might be no exception grew steadily stronger. Still, suspicion is not the same as proof. For years, the evidence was circumstantial. Sagittarius A was a bright radio source. The galactic center was crowded and strange. Quasars hinted at black holes elsewhere. But only when the orbits of stars were mapped with extraordinary precision did suspicion turn into certainty. The monster revealed itself not by being seen directly, but by the way it tugged on everything around it. For Andrea Ghez and Reinhard Genzel, this work became a decades-long pursuit. Their teams refined techniques of adaptive optics, correcting for the blurring effect of Earth's atmosphere to see the galactic center more clearly. They took thousands of measurements, plotted the positions of stars, and drew their paths like cartographers mapping an invisible whirlpool. When the data was finally assembled, the conclusion was unavoidable. A supermassive black hole was hiding there. In 2020, both Ghez and Genzel were awarded the Nobel Prize in Physics for this work, a recognition of the painstaking patience it took to confirm what had long been suspected. It is worth pausing to notice how suspicion often works in science. Rarely does discovery come in a single flash of certainty. More often it begins with hints, with anomalies, with signals that don't quite fit expectations. Sagittarius A was first a source of static in a radio receiver, then a bright spot on a catalogue, then a region of fast-moving stars, and finally a confirmed black hole. Each stage built on the last, suspicion hardening into conviction through decades of careful observation, and yet, even now, the suspicion has not entirely gone away. We are certain Sagittarius A is a black hole, but what exactly lies beyond its event horizon remains mysterious. Some physicists speculate about singularities, others about exotic states of matter, others about the need for new theories that go beyond Einstein's equations. The suspicion that something more is lurking continues, though now it is aimed not at the existence of the black hole itself, but at the nature of what black holes truly are. When we talk about how astronomers first suspected a monster was lurking, we're also talking about human imagination. The very idea of a black hole once seemed absurd. Einstein himself doubted that nature would allow them to form, yet little by little, the evidence piled up until denial was no longer possible. What began as suspicion became discovery, and what began as static in a radio antenna became the confirmation that at the centre of our galaxy sits a supermassive black hole, patient and immense, quietly shaping everything around it. The suspicion of something monstrous at the core of the Milky Way is a reminder that the universe often hides its most profound secrets in plain sight, visible only if we learn to look with new kinds of eyes. It also reminds us that discovery is not always about finding something new. Sometimes it is about recognizing what has been there all along, waiting for us to notice. When astronomers first turned their attention to the centre of the Milky Way in detail, it wasn't what they could see that convinced them something extraordinary was hidden there. It was what the stars were doing. In the quiet suburbs of our galaxy, where the sun resides, stars drift slowly, taking hundreds of millions of years to circle the galactic centre. Their motion is steady, almost leisurely, following the broad sweep of gravity created by the mass of billions of stars and clouds of gas. But when telescopes focused on the crowded core, the picture changed. Some stars there were racing at unimaginable speeds, whipping around invisible points as if caught in the grip of something much heavier than anything visible. It was these strange orbits, recorded with patience over decades, that gave the secret away. The idea is simple in principle. By watching how stars move, you can infer what is pulling on them. It is the same logic Isaac Newton used to explain the orbit of the moon, or Johannes Kepler applied to the motion of planets centuries earlier. Objects move in response to gravity, and the tighter and faster the orbit, the stronger the gravity must be. So, when astronomers began carefully charting the orbits of stars in the galactic centre, they were in effect weighing an invisible object. The surprise was not that something was there, but how much mass was crammed into such a small space. The stars that provided the most striking evidence are known collectively as the S-stars, a group of young, hot, massive stars found very close to the galactic centre. Among them, one stand out, S2. This star is about 15 times the mass of our Sun and shines brightly in the infrared. What makes it extraordinary is its orbit. Every 16 years, S2 swings in close to Sagittarius A, passing within just 17 light hours of the black hole. That's about 3 times the distance between the Sun and Pluto. For a galaxy, that is breathtakingly close. At its nearest approach, S2 hurtles through space at more than 7,000 kilometers per second, fast enough to travel from Earth to the Moon in under a minute. No ordinary mass could make a star move that way. Watching S2's orbit over time was like drawing a map of the invisible. Astronomers tracked its position year after year, sometimes night after night during crucial periods, plotting its path as it swooped in and sped back out. The orbit formed a long ellipse, precisely the kind of shape predicted by Newtonian mechanics for an object bound by gravity. But the sheer speed and tightness of the curve revealed the mass at the centre. By fitting the orbit with equations, astronomers calculated that the unseen object must weigh 4 million times as much as the Sun, and yet be contained within a region smaller than our solar system. That density left only one possible explanation: a supermassive black hole. S2 was not the only star to reveal this story. Other S-stars have been tracked, each with their own dramatic orbits. Some swing in even closer than S2, though on longer timescales that take decades to unfold. Together, Their paths weave a picture of a central mass that cannot be explained away by clusters of smaller objects. If the mass were a dense group of neutron stars or stellar remnants, they would quickly collide and collapse under their own gravity. Only a black hole could remain so compact, so stable, and so invisible. The orbits also gave scientists a way to test Einstein's theory of general relativity in an extreme environment. According to relativity, space and time are curved by mass, and the stronger the gravity, the more noticeable the effect. When S2 made its close approach in 2018, astronomers observed a phenomenon called gravitational redshift. The star's light was stretched to longer wavelengths as it climbed out of the intense gravitational field. This was exactly what Einstein's equations predicted, and it was the first time such an effect had been measured in the orbit of a star around a supermassive black hole. The strange orbits didn't just reveal the mass of Sagittarius A, they also confirmed the physics of how gravity works in its vicinity. It is striking to consider how much patience was required to reach these conclusions. An orbit of 16 years is a long time for a human career, and longer orbits take even more dedication. Astronomers had to build instruments capable of resolving stars separated by tiny angles in the sky, the equivalent of distinguishing individual headlights on a car thousands of kilometers away. They had to return night after night, year after year, assembling a record that could not be faked or guessed. The strange orbits unfolded slowly but with certainty until the evidence was undeniable. And yet, as with so many discoveries, the orbits raised new questions. The S-stars themselves are unusual. They are young, massive and hot, but star formation near a supermassive black hole should be difficult. The tidal forces should tear apart the gas clouds before they can collapse into stars. So how did these stars get there? Were they born farther away and then migrated inward through gravitational interactions? Or is there some hidden mechanism that allows stars to form in spite of the odds? Astronomers continue to debate the answer. The orbits gave away the presence of the black hole, but they also revealed puzzles about the environment around it. The strangeness goes deeper. Some stars appear to move on paths that are not neatly aligned, as if their orbits were tilted at odd angles to one another. This suggests a history of dynamical interactions, perhaps involving past clusters or disrupted systems. Others hint at even subtler effects, like precession, the gradual shifting of an orbit's orientation due to the warping of spacetime. Detecting these tiny changes requires extraordinary precision, but they could provide yet more tests of relativity, and perhaps even clues about new physics. To the untrained eye, watching stars orbit may not seem dramatic, but in the context of the galaxy, these are some of the most extreme motions ever observed. Our Sun takes about 230 million years to circle the Milky Way once. S2 does it in just 16 years, and other S-stars in similar timescales. Their strange orbits are like fast-forwarded versions of galactic dynamics, condensed into spans we can witness within a lifetime. By studying them, we are not just learning about Sagittarius A, but also about how stars and black holes interact across cosmic history. It is also worth reflecting on how indirect the evidence is. We cannot see the black hole. We cannot send a probe into its event horizon, or watch light escape from its surface because there is no surface. Instead, we watch stars dance around an invisible partner, and from the shape of the dance we deduce the partner's nature. It is like watching shadows on a wall and inferring the shape of the unseen puppet behind them. The strange orbits gave away the black hole not because we saw it directly, but because nothing else could explain the choreography. The story of these orbits also highlights the international and collaborative nature of modern astronomy. Teams from around the world, using telescopes in Chile, Hawaii and elsewhere, pooled their data, refined their methods, and cross-checked results. The picture that emerged was not the work of one person or one night, but of decades of global effort. The strange orbits became not just a scientific revelation, but also a testament to human persistence. For those listening now, it may be comforting to think about how something so immense, so incomprehensible, was revealed by such careful, almost patient observation. No explosions or sudden discoveries, just the steady plotting of points on a graph, night after night, year after year, until the invisible became undeniable. It is a reminder that not all monsters are uncovered with drama. Some reveal themselves slowly, in the quiet arcs of stars across the sky. And as those arcs continue, they will keep teaching us. Every new orbit brings fresh data. Every close pass reveals another nuance. The strange orbits that gave the secret away are still unfolding, and astronomers are still watching, still refining, still wondering. When we talk about black holes, it is tempting to imagine them as all being the same kind of thing, like stars or planets, differing mainly in size. But just as there are many types of stars, from small red dwarfs to blazing blue giants, there are different categories of black holes. Some are formed in the collapse of massive stars at the end of their lives. These stellar black holes may contain a few times the mass of our Sun, perhaps 10 or 20, sometimes more, but they remain relatively small on a cosmic scale. Others, rarer but even more puzzling, fall into what astronomers call the intermediate category, bridging the gap between stellar and truly giant black holes. And then there are the titans, the ones that weigh millions or even billions of solar masses, the supermassive black holes that dominate the centres of galaxies. Sagittarius A belongs to this last category. Understanding what makes it supermassive, rather than just ordinary, is a way of understanding not only the black hole itself, but also the role it plays in the life of the Milky Way. To grasp the distinction, it helps to begin with the numbers. A stellar black hole, the kind created when a massive star collapses, might be about 20 kilometers across, with the mass of perhaps 10 suns. Sagittarius A, by contrast, contains about 4 million suns worth of mass. Its event horizon, the point of no return, spans roughly 25 million kilometers. That sounds large, and it is, but compared to its mass, it is still tiny. The Earth orbits the Sun at about 150 million kilometers. If you replace the Sun with Sagittarius A, its event horizon would still fit comfortably inside Earth's orbit. 4 million times the mass of the Sun, packed into a space smaller than our solar system, is the very definition of supermassive. What makes Sagittarius A supermassive is not just the scale of its mass, but the way it must have grown. A stellar black hole is the predictable result of a star's death. When a star much larger than our Sun runs out of fuel, its core collapses, and if the mass is high enough, nothing can stop gravity from squeezing it into a singularity. But there is no single star, nor even a group of stars that could collapse into something as large as Sagittarius A. To reach millions of solar masses, a black hole must feed, merging with other black holes, swallowing gas and dust, consuming stars and perhaps even forming from much larger seeds in the early universe. Its size tells us it has a long and dramatic history, stretching back to the dawn of the galaxy itself. Astronomers suspect that supermassive black holes like Sagittarius A may have formed very early in cosmic history, less than 1 billion years after the Big Bang. In those early times, enormous clouds of gas were collapsing to form the first galaxies. In some cases, those clouds may have collapsed directly into black holes thousands of times the mass of the Sun, skipping the intermediate steps. From there, the seeds grew larger as they pulled in surrounding matter, eventually reaching the millions of solar masses we see today. If this picture is correct, Sagittarius A has been with us since the beginning of the Milky Way, shaping its growth and anchoring its structure from the start. Another way to think about what makes Sagittarius a supermassive is to consider the influence it exerts. A stellar black hole can dominate a binary star system, pulling material off a companion star, but its reach is limited. Sagittarius A, by contrast, commands the motions of entire clusters of stars. The S-stars we discussed earlier, whipping around at breakneck speeds, are direct evidence of its enormous pull. Farther out, its gravity helps to organize the orbits of billions of stars, maintaining the spiral structure of the galaxy. Its mass is not just an oddity. It is a central feature of the Milky Way's architecture. The term supermassive also reflects how these giants behave differently from their smaller cousins. Because they are so large, the density at their event horizons is actually lower than that of a stellar black hole. Paradoxically, this means that an object falling into a supermassive black hole experiences less intense tidal forces at the horizon itself. You could in principle cross the event horizon of Sagittarius A without being instantly stretched into spaghetti, something that would be impossible for a stellar black hole. Of course, the fate awaiting you deeper inside would still be inevitable, but the distinction highlights how scale changes the very experience of gravity. Supermassive black holes also interact with their surroundings on much larger scales. When they feed actively, the matter swirling into them can release tremendous amounts of energy, sometimes in the form of powerful jets that shoot out from the galaxy's core. These jets can stretch for thousands of light years, carrying energy into intergalactic space. Sagittarius A is relatively quiet today, but evidence suggests that in the past it may have unleashed outbursts powerful enough to shape the Milky Way. Enormous gamma-ray bubbles observed above and below the galaxy are thought to be remnants of such activity, signs that the monster was once much hungrier. The supermassive label is therefore not just about size, but also about role. Ordinary black holes are fascinating in their own right, but they are like minor characters in the story of the cosmos. Supermassive black holes are the main players, the ones around which galaxies revolve. Without them, galaxies might not form the way they do. Without galaxies, stars like our Sun might not appear. Without stars, there would be no planets, no oceans, no listeners lying awake tonight, wondering about distant mysteries. The fact that Sagittarius A is supermassive is part of the reason we exist to notice it. Another striking difference between supermassive and stellar black holes is the way we detect them. A stellar black hole is often discovered when it interacts with a nearby star, producing bursts of X-rays as material falls in. Supermassive black holes, by contrast, reveal themselves through the motions of entire groups of stars, through the glow of accretion disks, through the structure of galaxies. Their signatures are grander, their footprints larger. Sagittarius A was confirmed not because we saw it directly, but because the orbits of stars demanded its presence. That demand, 4 million solar masses in such a tiny region, is what separates the supermassive from the ordinary. For astronomers, Sagittarius A is both a case study and a benchmark. It is the closest supermassive black hole to us, a laboratory for testing ideas that can be applied to others across the universe. Quasars in distant galaxies, blindingly bright, are powered by black holes billions of times the Sun's mass. But those are too far away to study in detail. Sagittarius A, quiet though it may be, is near enough for us to resolve individual stars, to track orbits, to measure flares. In that sense, it is our window into the class of supermassive black holes, the one example we can study with intimacy. Thinking about what makes Sagittarius A supermassive is also thinking about the difference between the ordinary and the extraordinary in the universe. The laws of physics are the same everywhere, but scale changes everything. Gravity that bends light around a stellar black hole bends entire galaxies around Sagittarius A. Accretion disks that glow for a single star's mass blaze with energies that can outshine galaxies when millions of solar masses are involved. The difference is one of magnitude, but magnitude makes the ordinary strange, and yet, even as we call it supermassive, Sagittarius A is modest compared to some of its peers. In other galaxies, black holes have been measured at billions of solar masses. Some weigh so much that they challenge our theories of how such giants could ever have formed. Sagittarius A is, in a sense, a middleweight. Not small, certainly not ordinary, but not the most extreme either. It is large enough to anchor our galaxy, but quiet enough to let life thrive in its arms. Perhaps that balance is part of the reason we are here at all. Meeting Sagittarius A as a supermassive black hole rather than an ordinary one reminds us that categories in astronomy are more than labels. They're insights into history, into structure, into the hidden connections between the tiniest particles and the largest structures. To call it supermassive is to acknowledge that it belongs to a class of objects that define the architecture of the universe. When people first hear the term black hole, their imagination often goes straight to the idea of a bottomless pit, something like a cosmic sinkhole pulling everything inward. In reality, it is not quite a hole in the ordinary sense, not a tunnel through space, but rather a region where gravity has grown so strong that nothing can escape. The defining feature of a black hole is not what lies inside, but the boundary around it, an invisible surface known as the event horizon. For Sagittarius A, this border of no return is the line that separates what can still communicate with the universe from what is forever hidden. To understand why this matters, we have to take a closer look at how gravity warps space and time at such extremes. Einstein's theory of general relativity tells us that mass and energy bend the fabric of space-time. The more concentrated the mass, the stronger the bend. For everyday objects like planets and stars, this bending creates the familiar sensation of gravity. But for a black hole, the mass is packed so tightly that the bending becomes infinite at the centre. The event horizon is the spherical boundary around this point where the escape velocity, the speed needed to break free from gravity, reaches the speed of light. Nothing can go faster than light, so once you cross the event horizon, there is no path back out. Even light itself is trapped. That is why the black hole appears black. It is not a physical surface you could touch, but rather a mathematical boundary, a horizon beyond which events cannot affect the outside world. For Sagittarius A, the event horizon stretches about 25 million kilometers across, or roughly the size of Mercury's orbit around the Sun. To put that in perspective, if you shrank the Earth into a black hole, its event horizon would be less than a centimetre across. The difference shows just how enormous Sagittarius A really is. Yet the principle is the same no matter the size. Once inside the horizon, all paths point inward. Space itself is tilted toward the centre. The border is absolute. What makes the event horizon so fascinating is not only what happens inside, but what happens just outside. Matter falling towards Sagittarius A forms an accretion disk, swirling at nearly the speed of light. As the gas spirals inward, it compresses and heats to millions of degrees, emitting radiation across the spectrum. The edge of the event horizon distorts the light, bending it around the black hole in ways that create strange illusions. To an outside observer, material near the horizon seems to slow down, its light stretched and dimmed by gravity, fading into redder and redder wavelengths. From our vantage point, nothing ever seems to cross the horizon completely. Instead, it lingers, frozen in time, even as in its own frame of reference it plunges inward in seconds. This contradiction, the difference between what an infalling object experiences and what a distant observer sees, is part of what makes black holes so counterintuitive. If you fell towards Sagittarius A, you would cross the event horizon without noticing anything special at that exact boundary. No wall, no jolt, no barrier. But you would never be able to send a message back. To those watching from afar, your signals would stretch out, slow down and fade, leaving the impression that you never truly crossed. The event horizon is a border of perception as much as of physics. Astronomers often describe the horizon as the ultimate veil. It hides whatever lies inside, whether a singularity of infinite density or some exotic new state of matter that we do not yet understand. No telescope can pierce it, no radiation can escape from within it, and yet, paradoxically, the horizon itself can be studied. The Event Horizon Telescope, a global network of radio dishes acting together, captured the silhouette of Sagittarius A by imaging the glow around it and the shadow cast by the horizon. The result was a ring of distorted light encircling a darkness, the outline of the border of no return. For the first time we could see the shape of the invisible, not directly, but through the way it bends the world around it. The event horizon also challenges our ideas of information and reality. According to classical physics, anything that falls in is lost forever, but quantum theory suggests information cannot be destroyed. This tension has led to one of the greatest puzzles in modern physics, the black hole information paradox. Does the horizon truly erase information? Or is it somehow encoded in the radiation emitted by the black hole known as Hawking radiation? For Sagittarius A, the effect would be far too faint to measure, but in theory, black holes slowly leak energy over unimaginable timescales, eventually evaporating. Whether information escapes with that radiation remains one of the deepest unsolved mysteries. For those trying to imagine the horizon, it helps to think of it as a one-way mirror. From outside, you can look toward it, though all you see is distortion and shadow. From inside, you cannot look back at all. Once crossed, every path forward leads deeper, and time itself seems to conspire against escape. The horizon is not a barrier like a wall of stone. It is a barrier like the end of a road, the point beyond which all directions slope downward. Sagittarius A's horizon is also unusual because of its sheer scale. For a small stellar black hole, tidal forces near the horizon are lethal. A human falling in would be stretched and torn apart before even crossing. But for a supermassive black hole, the gradient of gravity across your body is gentler at the horizon. You could cross it without noticing the tides immediately, though deeper in they would eventually overwhelm you. This strange fact means that supermassive black holes, for all their enormity, are in some sense kinder at the edge. The danger lies not in the crossing itself, but in what lies inexorably beyond. Scientists often say that the event horizon is where relativity meets quantum mechanics head-on. It is where space-time is bent to its limits, where our best theories give conflicting answers, where new physics might one day emerge. Sagittarius A, sitting quietly at the centre of the Milky Way, is not just a monster swallowing stars. It is also a natural laboratory, an experiment waiting for us to interpret. Every star that swings by, every flare of radiation, every photon bent around the horizon is a clue. From a philosophical point of view, the horizon also raises questions about the limits of knowledge. There is a region of the universe we can never see, never measure, never know directly. No matter how advanced our technology becomes, the interior of a black hole is beyond us. The event horizon is a cosmic reminder that some boundaries cannot be crossed, and yet it is also a reminder of how much we can still learn indirectly. The shadow image of Sagittarius A, the dance of stars near the core, the flickers of light from gas on the brink of falling in, all of these are ways of brushing against the edge of the unknowable. There is something absolute about it, a line drawn by nature itself. Outside, the galaxy spins, stars burn, planets orbit, life unfolds. Inside, all paths end, and in between, at the horizon, is a quiet limit, the boundary between the known and the unknowable. When you hear the phrase black hole, it's natural to imagine matter simply dropping into a void, as if stones were falling into a bottomless well. But in reality, the journey of matter falling into Sagittarius A is anything but simple. It is violent, luminous, and drawn out, a process that reveals some of the most extreme physics in the universe. To imagine what happens to matter as it falls in, we need to follow its path step by step, from the moment it drifts too close to the point where it finally disappears beyond the horizon. Most matter in the galaxy is in the form of gas and dust. These particles float through space in clouds, sometimes dense, sometimes thin, often stretching for dozens of light years. When such a cloud strays near the galactic centre, the gravity of Sagittarius A begins to tug at it. The gas is drawn inward, but it doesn't fall straight in. Instead, because matter in space almost always has some sideways motion, it begins to spiral. Like water swirling as it drains, the gas forms an accretion disk, a whirling flattened structure orbiting the black hole. This disk is the stage where most of the drama unfolds. As the gas spirals inward, friction between its layers heats it to extraordinary temperatures. Atoms collide violently, stripping electrons, creating plasma. The disk glows with radiation, shining brightest in X-rays. Paradoxically, the region around a black hole, the very thing we call dark, can become one of the brightest objects in the universe, outshining entire galaxies when the feeding is intense. Sagittarius A is relatively quiet compared to the blazing quasars in distant galaxies, but even so, when it consumes matter, it can flare with bursts of energy that we can detect across light years. For the matter itself, the journey is chaotic. Gas clouds are stretched and torn as tidal forces pull harder on one side than the other. Magnetic fields twist and snap, accelerating particles to near the speed of light. Jets of plasma can sometimes erupt perpendicular to the disk, blasting out into interstellar space. These jets are still not fully understood, but they are a common feature of accreting black holes. In the case of Sagittarius A, they may have been stronger in the past, powerful enough to carve structures in the galaxy that we can still see today. As matter moves closer to the event horizon, time and space behave strangely. From the perspective of an outside observer, the unfailing gas appears to slow down, its light stretched into redder wavelengths as it struggles to escape the gravitational field. Eventually the glow fades and the matter seems to freeze at the horizon, never quite crossing. But from the matter's own point of view, the plunge is swift and irreversible. It crosses the horizon in seconds, falling toward the singularity at the centre where, according to classical theory, it is compressed to infinite density. One of the most dramatic scenarios involves stars themselves. Occasionally, a star wanders too close to Sagittarius A and is caught by its gravity. If the star passes within a certain distance, tidal forces overwhelm its own gravity. The star is pulled apart in a process called spaghettification, stretched into a long stream of gas. Half of that gas is flung outward into space, while the other half spirals inward to feed the black hole. From Earth, astronomers can sometimes see these events as sudden flares of radiation, lasting months or years, as the star's remains are digested. These tidal disruption events are rare for Sagittarius A, but they are spectacular when they happen, cosmic meals too violent to go unnoticed. On smaller scales, even chunks of dust or asteroids that drift too close meet similar fates, shredded and vaporized before they can cross the horizon. The closer matter gets, the more extreme the conditions become. Temperatures soar to millions of degrees, pressures rise to unimaginable levels, and radiation is emitted in floods. The final moments before crossing the horizon are some of the most energetic in the universe, even though the end result is silence, with all signals swallowed. For scientists, following what happens to matter as it falls in is not just a matter of imagination. It is something they can study by watching the flickers of light and radio signals from Sagittarius A. Infrared and X-ray flares are like fingerprints of gas being consumed. By timing these flares and mapping their intensity, astronomers can reconstruct the behaviour of matter near the horizon. In recent years, some observations have even caught hints of hotspots orbiting close to the event horizon, glowing briefly before disappearing. These may be clumps of plasma circling the black hole, giving us a glimpse of the last dance before the plunge. There is also a strange paradox here. The matter that falls in is never seen again, yet its death throes light up the universe. Without the glow of the accretion disk, without the flares and jets, we might never know black holes existed. It is the act of destruction that makes them visible. In that sense, Sagittarius A is revealed to us not by what it is, but by what it consumes. The physics of this process also stretches our theories. General relativity predicts the overall shape of spacetime near the horizon, while plasma physics explains the behaviour of the accretion disk, and quantum mechanics suggests that information may not be truly lost. But uniting all these ideas into a single, complete picture is still beyond us. Matter falling into Sagittarius A is not just a physical event, it is a test of our deepest understanding of nature. Every flare, every hotspot, every distorted photon carries clues. It is tempting to imagine what it would feel like for matter itself. Of course, gas and dust do not feel in the way we do, but thinking of it in human terms helps bring the picture into focus. Imagine being stretched, pulled, and heated until your structure breaks down entirely. Your atoms scattered into plasma, your particles accelerated to nearly light speed. Imagine your glow being bent and twisted by gravity, some of it escaping into space, some of it circling endlessly before plunging in. The end is inevitable, but the path there is luminous, dramatic, and visible across thousands of light years. Sagittarius A's appetite is modest by cosmic standards. It is not swallowing stars every day, nor blazing like a quasar. But even small amounts of matter falling in produce measurable effects. Gas clouds drifting nearby can brighten it for weeks. A single flare can carry the energy of billions of nuclear bombs. For something so distant, so hidden, the signals are astonishingly clear. They remind us that the centre of the galaxy is not static but alive with activity, even if most of it lies beyond our eyes. What makes all of this especially compelling is that the process is universal. Every black hole, whether small or supermassive, shapes matter in this way. The details differ, the scales of time and distance change, but the essentials remain. Matter cannot simply fall quietly into a black hole. It must orbit, spiral, heat, glow, and only then vanish. To watch Sagittarius, a feed is to watch the laws of physics play out in their most extreme form, and yet, even as we understand the broad strokes, mysteries remain. Why do some flares happen suddenly while others build slowly? What sets the timing of hotspots? How do magnetic fields shape the jets? How exactly does matter behave as it approaches the horizon in its final moments? These are questions scientists are still working to answer, piecing together clues from telescopes on Earth and from simulations on supercomputers. Matter falling into Sagittarius A is not just a spectacle. It is a puzzle, one we are still learning to solve. For us, lying here on a small planet far away, it can be strangely calming to think of matter being drawn into the black hole at the centre of the galaxy. It is a process that has gone on for billions of years, long before humans existed, and will continue long after we're gone. The dust and gas that fall in today are part of a cycle as old as the galaxy itself. In some sense, even destruction is part of creation, for the energy released shapes the environment, stirs the gas, and influences the formation of new stars. The monster devours, but in devouring it helps to sculpt the Milky Way. When we picture a black hole, the mind jumps first to darkness, to something invisible and silent, swallowing everything without a trace. But the reality is more complicated. A black hole cannot be seen directly, but the environment around it can be dazzling. Matter on its way inward does not fall quietly. It spirals, collides, compresses and heats until it glows with some of the brightest light in the universe. Around Sagittarius A, this glow is faint compared to the blinding quasars in other galaxies, but it is still enough to reveal the black hole's presence. The accretion disk, the thin whirling sheet of matter orbiting just outside the event horizon, and the flares that sometimes erupt from it, are the lanterns we use to see the monster in the dark. The story begins with the disk itself. Imagine gas and dust drifting toward the galactic center. Each particle carries some sideways motion, some angular momentum, so it cannot fall straight in. Instead, gravity pulls it inward while its sideways speed keeps it circling, forming a flattened spiral. Friction between layers of gas combined with magnetic turbulence robs the material of energy, causing it to spiral closer and closer. The process is chaotic, but the result is a stable disk, glowing because the gas is heated to millions of degrees. In Sagittarius A, the accretion disk is relatively small in cosmic terms, but it is enough to make the black hole one of the strongest radio sources in the sky. To understand how bright these disks can be, it helps to consider efficiency. When matter falls into a black hole, it converts a fraction of its mass into energy, not through nuclear fusion like stars, but through pure gravitational compression. The efficiency is staggering. Up to 10% of the matter's mass can be radiated away, compared to less than 1% for nuclear fusion in stars. This means that black holes, paradoxically, can outshine anything else in the universe, not by emitting light themselves, but by lighting up what falls toward them. Sagittarius A is in a low-feeding state, often described as quiescent. Most of the time, its disk is dim, glowing steadily in radio and faintly in X-rays, but occasionally it flares. These flares are sudden outbursts of light, lasting from minutes to hours, in which the brightness increases by factors of tens or even hundreds. Astronomers have watched them with infrared and X-ray telescopes, recording their rise and fall like heartbeat spikes. The cause is not always clear. Some flares may come from clumps of gas heating up as they spiral inward. Others may be triggered by magnetic reconnection events, where twisted magnetic fields snap and release energy. Whatever their source, they are reminders that Sagittarius A is not asleep but dozing, capable of waking with bursts of energy that travel across light years. To an observer near the black hole, the glow of the disk would be unlike anything familiar. The light would not spread evenly but would be distorted by gravity. Photons leaving the far side of the disk would be bent around, making the disk appear to curve up and over the black hole, as if you could see both its front and its back at once. The side rotating toward you would appear brighter because of relativistic beaming, while the side rotating away would dim. The result would be a glowing ring, brighter on one edge, encircling a shadow of darkness. This is exactly the image captured by the Event Horizon Telescope, a distorted halo marking the glow of the accretion disk around Sagittarius A. Flares make the glow even stranger. In 2018, astronomers recorded a bright infrared flare that seemed to trace the orbit of a hotspot circling close to the event horizon. It lasted less than an hour, but during that time, the hotspot appeared to orbit the black hole at nearly a third of the speed of light. To see such a thing is to glimpse matter at its most extreme, glowing brightly for a brief moment before vanishing. These hotspots may be common, little knots of plasma that form and dissolve, each adding its brief spark to the larger glow. The glow around Sagittarius A is not just light, it is also radio waves, emitted by electrons spiraling in magnetic fields at near-light speeds. These signals were the first hints of its presence, detected long before we knew about black holes. Even today, radio telescopes are among the best tools for studying the galactic center, since radio waves can slip through the dust that blocks visible light. The flares in radio, though fainter than in infrared, provide a complementary view, helping scientists piece together the full picture. For us watching from across 26,000 light-years, the glow is subtle. Sagittarius A is faint compared to the stars in the sky. You cannot look up and see it with your eyes, but to sensitive instruments it is a restless ember, flickering irregularly, reminding us that the monster is alive. The glow is not constant because the feeding is not constant. Gas clouds drift in irregularly, stars wander close unpredictably, magnetic fields twist and snap at random. The glow is the signature of chaos, shaped by gravity, turbulence, and chance. It is also a source of clues. By analysing the timing and spectrum of the flares, astronomers can test the predictions of general relativity and strong gravity. The way the light shifts, the way it decays, the way it oscillates, all encode information about the space-time near the horizon. In that sense, every flare is not just a spark of brightness, but a data point, a tiny experiment performed by nature and read by our telescopes. Some theorists even suggest that flares may help reveal whether Sagittarius A harbours features beyond what Einstein's theory predicts. If there are subtle deviations, if gravity behaves differently near the horizon than expected, the flares might show it. So far, relativity has passed every test, but the glow continues to offer opportunities to push deeper, to search for cracks in our understanding. From a human perspective, there is something poetic in the idea that destruction produces beauty. The gas that falls into Sagittarius A is torn apart, heated, and annihilated, yet in the process it glows with light we can detect across the galaxy. The flares are violent, but from our distance they are gentle flickers, visible only through careful instruments, arriving as faint signals that we can translate into knowledge. The monster devours, and in devouring, it lights itself with a halo. For those drifting off to sleep, this image may feel oddly comforting. The universe is full of darkness, yet around even the darkest places light finds a way to shine. The glow of Sagittarius A is not a steady beacon but a flicker, irregular and unpredictable, like the dying embers of a fire. And yet those embers carry secrets, revealing the shape of space-time, the behaviour of plasma, the reach of gravity. The glow is both a warning and an invitation, a reminder of what lies beyond our sight and what we can still learn. Long before astronomers could take pictures of Sagittarius A, long before the orbits of the S-stars were mapped, or the flares of the accretion disk were recorded, the first hints of something unusual at the heart of the galaxy came not as light, but as whispers. These whispers were carried on radio waves, signals from the galactic centre that reached Earth quietly but insistently, like static in the background of the cosmos. They were faint, they were puzzling, and they became the first clues that a hidden power lived at the core of the Milky Way. In the early 1930s, a radio engineer named Karl Jansky was asked to study the sources of interference that plagued long-distance communications. Using a large rotating antenna, he catalogued the hiss and crackle that disrupted radio signals. Some of it came from storms on Earth, some came from equipment. But a portion of the static repeated with a cycle of about 23 hours and 56 minutes, the sidereal day, the period it takes Earth to rotate relative to the stars, not the Sun. This clue told him that the interference was extraterrestrial. By tracking the signal, Jansky realised it came from the direction of the constellation Sagittarius, the very region of sky where the centre of the Milky Way lies. At the time, the discovery was revolutionary. No one had expected the universe to speak in radio waves. Telescopes revealed stars in visible light, but the idea that space was filled with other kinds of signals was new. Jansky's equipment was crude by modern standards, yet it revealed the first whispers from the galactic centre. He didn't know what they meant, and the term black hole hadn't even been coined yet, but the trail had been opened. In the decades that followed, radio astronomy blossomed. Larger and more sensitive dishes were built, capable of resolving finer details and detecting weaker signals. When astronomers pointed them at Sagittarius, they found a strong compact radio source at the very centre of the galaxy. They named it Sagittarius A. Later refinements reveal that Sagittarius A was itself complex, with a particularly bright core now called Sagittarius A. The asterisk was added to mark it as unique, a way of saying this was the true centre of the signal, the heart of the whispers. The nature of those whispers was puzzling. Sagittarius A was small in apparent size, meaning the source had to be compact. It was also steady over long periods, unlike the variable radio burst of pulsars. Whatever was making the signal was unlike ordinary stars or nebulae. The compactness, the intensity, and the central location all pointed towards something exotic. Long before the orbits of stars confirmed it, Sagittarius A was already hinting at a supermassive black hole. The radio waves themselves are created by electrons spiralling through magnetic fields at nearly the speed of light, a process called synchrotron radiation. As matter falls towards Sagittarius A, it heats and ionizes, and the charged particles accelerate, emitting radio waves that travel freely through the galaxy. Unlike visible light, which is blocked by the dense clouds of dust between us and the centre, radio waves slip through almost unhindered. That is why they became our first direct connection to the hidden heart of the Milky Way. Over the years, the whispers have revealed more than just presence. By studying the spectrum of radio waves, astronomers have inferred the density and temperature of the gas near the black hole. By monitoring fluctuations, they have tracked storms of plasma, the twisting of magnetic fields, and even the possibility of hotspots orbiting close to the horizon. The whispers carry stories about turbulence, about chaos, about energy being released in the final moments before matter is consumed. In the 1970s, a young astronomer named Bruce Ballack and his advisor Robert Brown used the National Radio Astronomy Observatory to make more detailed observations. They confirmed that Sagittarius A was extremely compact, no larger than the orbit of Mercury. The intensity of the radio waves from such a small region was staggering, and the idea that it might be a supermassive black hole began to take hold more firmly. The whispers were not just noise, they were the first clear signals of the monster at the centre. Listening to the galactic centre through radio telescopes is a very different experience from looking through optical ones. Visible light gives sharp, bright points. Radio waves arrive more diffuse, requiring careful processing to turn into images. The antennas must be spread over wide areas, sometimes continents apart, and their data combined through a technique called interferometry. By linking telescopes across the Earth, astronomers create what is essentially a planet-sized ear, sensitive enough to hear the faintest whispers from 26,000 light-years away. This method reached its peak with the Event Horizon Telescope. By coordinating observatories from Hawaii to Spain to Antarctica, astronomers used Earth itself as a vast interferometer. The result was the image of Sagittarius A's shadow, outlined by the glowing radio emission from the accretion disk. Without those whispers, stitched together across the globe, the image would have been impossible. The whispers are not steady. They rise and fall, sometimes flaring, sometimes quieting. These variations provide insight into the feeding habits of Sagittarius A. When a clump of gas drifts inward, the radio emission brightens as electrons spiral faster and fields twist tighter. When the feeding slows, the whispers dim. The galaxy's heart is like a fire that rarely blazes but always smoulders, sending out sparks that our instruments can catch. For scientists, each whisper is precious. They arrive faint, distorted by the interstellar medium, scattered by turbulence along the way. Correcting for that scattering is like listening to a voice echoing through a canyon, trying to reconstruct the original words. Yet with clever techniques, astronomers do just that, extracting meaning from the faintest signals. The whispers also reach us with a kind of intimacy. Unlike the blinding glare of quasars in other galaxies, Sagittarius A's radio voice is quiet enough to study closely. It is nearby, by cosmic standards, close enough to allow detailed mapping of its behaviour. Through radio astronomy, the monster is not distant myth, but familiar presence, a steady hum beneath the background noise of the universe. For anyone lying awake, it can be strange to think that right now, as you listen, radio waves from the galactic centre are washing over Earth. They arrive continuously, passing through walls, through skin, through everything unnoticed. They have travelled for 26,000 years to reach us, and yet they arrive as faint as static. The galaxy whispers, and we are always bathed in its signal, whether we are aware of it or not. The story of these whispers connects technology and curiosity in a unique way. They were discovered not by someone looking for cosmic monsters, but by someone trying to improve telephones. They became the foundation of an entire new branch of astronomy, and they remain the most reliable way we have of eavesdropping on Sagittarius A. Every flare, every variation, every subtle shift in frequency is another word in a conversation we are only beginning to understand. For most of the history of astronomy, black holes lived only in equations and in the imagination. They were predictions of relativity, mathematical curiosities, supported indirectly by evidence but never seen. By definition, nothing can escape from a black hole, not even light, so how could anyone hope to take its picture? And yet, against all odds, humanity did exactly that. In 2019, the world saw the first image of a black hole's shadow in the galaxy M87. And in 2022, we finally saw our own, the dark heart of the Milky Way, Sagittarius A. To take a picture of something invisible required not just technology, but patience, creativity, and a collaboration stretching across the entire globe. The challenge begins with scale. Sagittarius A is 4 million times the mass of the Sun, but it sits 26,000 light-years away. Its apparent size in the sky is comparable to that of a bagel placed on the Moon. To resolve such a tiny shadow, you would need a telescope the size of Earth itself. Since building a telescope that large is impossible, astronomers used a clever workaround: very long baseline interferometry. By linking radio telescopes spread across the planet, they created an Earth-sized virtual dish. Each telescope recorded signals from Sagittarius A, and later, supercomputers combined the data into a single image. This project became known as the Event Horizon Telescope, or EHT. It brought together observatories from Chile, Spain, Mexico, Hawaii, Arizona, and even the South Pole. Each location contributed its own piece of the puzzle, recording petabytes of data onto hard drives. Because the amount of information was so huge, it couldn't be sent over the internet. Instead, the drives were physically flown to processing centers. The result was a dataset unlike anything astronomy had ever attempted. Even then, the task was daunting. Sagittarius A posed special challenges compared to the black hole in M87. For one, it is smaller, so matter orbits around it much more quickly. The hot gas near the event horizon can complete a circuit in minutes, meaning the image changes as you try to capture it. It's like trying to photograph a candle flame in the wind. On top of that, the signals were distorted by the interstellar medium, the gas and dust between us and the galactic center. Correcting for these effects required new algorithms, designed not just to sharpen an image but to reconstruct one from incomplete and shifting data. The final picture was released in May 2022. It showed what had long been expected: a glowing ring of light surrounding a dark central shadow. The shadow was not the black hole itself, but the silhouette of the event horizon against the background of glowing plasma. Light bent by gravity traced arcs around the black hole, creating the ring. For the first time, we were not just inferring Sagittarius A from orbits or whispers, we were seeing its outline. The image may have looked blurry to the casual eye, but to scientists it was astonishingly precise. The size of the shadow matched predictions from Einstein's equations almost perfectly. The brightness of the ring, the asymmetry of its glow, all lined up with simulations of how light should behave near a black hole. After decades of suspicion, after years of indirect evidence, the invisible had become visible, not in detail but in outline, enough to confirm the reality of what theory had demanded. The process of creating that image was as remarkable as the result. Hundreds of scientists around the world worked for years to design algorithms, calibrate instruments, and process the data. They intentionally divided into independent teams to reconstruct the image separately, ensuring that no bias shaped the outcome. When the teams finally compared results, the images matched. The blurry ring was not an artifact of imagination. It was real, and it was Sagittarius A. The significance of that picture goes beyond the beauty of seeing something hidden. It is a test of our deepest theories. Black holes are places where relativity reigns supreme, where space and time are bent to their limits. By measuring the size of the shadow, scientists confirm that Einstein's predictions held true even in this extreme environment. Any deviation could have hinted at new physics, but none were found. At least for now, relativity stands unchallenged at the edge of the abyss. For many people, though, the image was powerful for a different reason. It was the first time we could point to the center of our own galaxy and say, this is what it looks like. The Milky Way, the band of stars our ancestors mapped with myths and stories, has a heart. That heart is dark, but it casts a shadow surrounded by light. To see it, even blurred, is to feel a connection across scales, from a small planet to the centre of a galaxy, 100,000 light-years across. What does it mean to take a picture of something invisible? It means tracing not the thing itself, but its effect. The black hole remains hidden, but the light around it bends, glows, and outlines its presence. It is like looking at wind not directly, but by the way it ripples the grass. The EHT captured not the black hole, but the way light dances in its grip. That is the picture we now have pinned on our walls, the shadow of the monster devouring our galaxy. The success of imaging Sagittarius A also opens the door to future work. The current image is just the beginning, a snapshot blurred by limitations. As technology improves, the EHT and its successors will produce sharper views, perhaps even movies showing the accretion disk in motion. Already, astronomers are planning upgrades that will add more telescopes, more sensitivity, and wider frequency coverage. One day, we may watch Sagittarius A flicker and flare in real time, a cosmic fireplace burning at the centre of our home. It is worth reflecting on how much human effort it took to see this. The black hole has been there for billions of years, silent and steady. For most of that time, no eyes saw it, no ears heard it, no minds imagined it. Only in the past century have we begun to piece together its presence. Only in the past few years have we turned those whispers and orbits into an image. To take a picture of the invisible required not just instruments, but cooperation, trust, and persistence across cultures and continents. It is as much a story of humanity as it is of physics. Imagining this, the image itself may seem simple. A blurry orange ring around a dark circle, but behind it lies decades of suspicion, discovery, patience, and ingenuity. It is a reminder that sometimes the invisible can be brought into sight not by force but by collaboration. The monster at the heart of our galaxy is no longer just theory. It has a face, however blurred. When we speak about Sagittarius A, it is tempting to think of it as unique, the monster at the centre of our galaxy, the one black hole that holds us all in its grip. But Sagittarius A is not alone. Every large galaxy we have studied carefully seems to have a supermassive black hole at its heart. Some are smaller, some are vastly larger, some blaze furiously, while others sit in quiet repose. By comparing Sagittarius A to its kin, we learn not only about our own galactic centre, but also about the family of giants that shape the cosmos. Let us begin close to home, within the local group of galaxies. Our nearest large neighbour, Andromeda, hosts a central black hole that outweighs Sagittarius A by a factor of about 30. Where ours contains 4 million solar masses, Andromeda's is estimated at around 140 million. That difference is significant. It means the gravitational anchor in Andromeda is much stronger, shaping the stars of its bulge with a more commanding pull. Yet in some ways, the two galaxies' black holes behave similarly. Both are relatively quiet now, accreting little matter, emitting only faint radio signals compared to the blazing quasars found elsewhere. They are like siblings of different sizes, each holding their respective families of stars together. Farther out, we find truly enormous examples. In the giant elliptical galaxy M87, about 55 million light-years away, the central black hole tips the scales at more than 6 billion solar masses. This was the first black hole ever imaged directly, the one whose shadow the Event Horizon Telescope revealed in 2019. Compared to Sagittarius A, M87's black hole is a leviathan. Its event horizon would stretch beyond the orbit of Pluto if placed in our solar system. It also feeds more actively, producing a jet of particles that blast thousands of light-years into space, visible even in ordinary telescopes as a thin beam piercing the galaxy. Where Sagittarius A whispers, M87's black hole roars. And then there are even greater monsters. In the centres of some quasars, black holes weighing tens of billions of suns drive luminosities so intense they outshine the combined light of every star in their host galaxies. These are cosmic furnaces, their accretion disks blazing brighter than entire galaxies. By comparison, Sagittarius A seems modest, even restrained, a quiet giant in a quiet phase. It reminds us that black holes come in many temperaments. Some feed ravenously, others sparingly, some blaze with fury, others smoulder gently. The differences are not only in mass and brightness, but also in environment. Sagittarius A lives in a spiral galaxy, surrounded by a disk of stars and gas, with relatively calm conditions in its outer arms where we reside. Black holes in elliptical galaxies like M87 inhabit a very different setting, one filled with hot gas and chaotic stellar motions. These differences shape how the black holes feed, how often they flare, and how dramatically they affect their galaxies. Despite these variations, there are striking similarities. Everywhere we look, the relationship between a galaxy and its central black hole seems intimate. The mass of the black hole correlates closely with the mass of the galaxy's central bulge of stars. This suggests a deep connection. Galaxies and their black holes grow together, influencing one another's evolution. Sagittarius A, though small compared to some of its peers, fits this pattern. It is not an exception, but part of a cosmic rule, evidence that supermassive black holes are fundamental to galactic life. Another point of comparison lies in their histories. Evidence suggests that many supermassive black holes were far more active in the past. Quasars, common in the early universe, are rare today, implying that black holes used to feed more vigorously. Sagittarius A too shows signs of having been brighter and more energetic in the past. The enormous gamma-ray bubbles extending above and below the Milky Way may be remnants of ancient outbursts. Comparing Sagittarius A with more active black holes elsewhere helps astronomers piece together its biography, showing that our monster may once have been louder, though today it rests in relative quiet. There is also the matter of scale in perception. When astronomers look at distant quasars, the black holes are so far away that they appear as points of light. We can study their spectra, measure their luminosity, and model their jets, but we cannot track individual stars orbiting them. With Sagittarius A, we have the opposite advantage. Its closeness allows us to follow the S-stars, to measure their orbits, to see the flares in detail. Though smaller and quieter, it provides a laboratory for black hole physics that distant titans cannot. In that sense, Sagittarius A is special not because of its size, but because of our proximity. For those who wonder about danger, comparisons also offer reassurance. Some black holes in other galaxies are so active that they reshape their environments violently, blasting out jets and winds that sterilize regions thousands of light years across. If Sagittarius A behaved that way today, life on Earth might face severe consequences. But our black hole's relative quiet has allowed the galaxy's spiral arms to nurture stars, planets, and eventually us. By luck or by natural rhythm, we live in a galaxy whose monster sleeps more often than it feeds. Comparing Sagittarius A to others also highlights just how varied black holes are. There is no single model, no single outcome. Some galaxies host two black holes, the remnants of past mergers. Some may harbour intermediate mass black holes, filling the gap between stellar and supermassive. Sagittarius A sits comfortably in the middle of this spectrum, neither the smallest nor the largest, neither the hungriest nor the most dormant. Its role is steady, central, essential, but not extreme compared to its peers. From a cosmic perspective, this diversity is vital. By studying Sagittarius A in detail, and comparing it with giants like M87 and the quasars of the distant universe, astronomers can test theories across scales. The physics of accretion, of relativity, of jets and flares is the same everywhere, but the way it plays out depends on size, feeding rate, and environment. Sagittarius A provides the close-up view, others provide the wide-angle context. Together, they give us a fuller picture of what black holes are and how they shape the cosmos. Our galaxy's monster may seem enormous, but in the family of supermassive black holes, it is only one sibling among many, not the largest, not the smallest, simply our own. Knowing that the universe is full of them, each anchoring a galaxy, makes the cosmos feel more interconnected. Just as every city has its central square, every galaxy seems to have its central abyss. Sagittarius A is ours, and across the universe, billions of others are doing the same work, holding their galaxies together. When we think about black holes, it is natural to picture them as consumers, as cosmic drains that swallow whatever comes near. They're often described as destroyers, objects that erase stars, devour light, and trap time itself. But when astronomers began to study them more closely, they discovered something surprising. Black holes are not only ends, they're also shapers, especially the supermassive ones at the centres of galaxies like Sagittarius A. Do far more than sit quietly as gravitational anchors. They influence the lives of galaxies in profound ways, guiding their growth, regulating their stars, and shaping their destinies across billions of years. One of the first hints of this role came from the discovery of quasars. In the 1960s, astronomers detected objects so bright they outshone entire galaxies. Their spectra revealed that they were extremely distant, which meant their luminosity was staggering. The only explanation was that they were powered by matter falling into supermassive black holes. The energy released in this process was enough to light up the cosmos. These discoveries forced scientists to recognize that black holes could not remain passive. They could, when fed, dominate their surroundings. If quasars could shape galaxies in the early universe, then the quieter, supermassive black holes in today's galaxies might still be influencing their homes in subtler ways. Over time, more evidence accumulated. Astronomers noticed a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge of stars. This relationship, now known as the M-sigma relation, suggests that galaxies and their black holes grow together. A small galaxy tends to have a small black hole. A large galaxy tends to have a large one. The connection is too precise to be coincidence. It means that somehow, the growth of stars and the growth of the central black hole are linked, even though the black hole is tiny compared to the galaxy as a whole. How does this link work? The answer lies in feedback. When matter falls into a supermassive black hole, it does not all vanish silently. Much of it is heated and accelerated, releasing energy back into the surrounding galaxy. Sometimes this energy emerges as radiation. Sometimes it takes the form of winds that blow gas outward. Sometimes it is focused into jets, narrow beams of plasma that pierce thousands of light years into intergalactic space. These outflows can regulate how stars form. Too much gas flowing outward can quench star formation by blowing away the raw material. In other cases, the compression of gas by shockwaves can trigger bursts of new stars. The black hole becomes not only a consumer, but also a gardener, pruning and nurturing the galaxy's growth. Sagittarius A offers a quieter example. It is not a quasar. Its feeding is modest, yet even at low levels it influences the Milky Way. Evidence suggests that a few million years ago, Sagittarius A may have unleashed an outburst strong enough to inflate the enormous gamma-ray bubbles we see today extending above and below the galactic plane. These bubbles, stretching tens of thousands of light years, are relics of feedback, proof that even our relatively calm black hole has had moments of dramatic influence. Such events could have stirred the interstellar medium, altered patterns of star formation, and shaped the structure of the galaxy we inhabit. On smaller scales, black holes can sculpt the very centres of galaxies. In the crowded environments near their horizons, stars are tossed about by gravity, sometimes flung outward in slingshot trajectories, sometimes torn apart and consumed. Gas clouds are heated, ionized, and redistributed. This constant stirring prevents galactic centres from becoming too static. They remain dynamic, turbulent places, with the black hole as both conductor and participant in the orchestra. The shaping power of black holes is not limited to violent episodes. even their quiet gravitational presence has effects. The orbits of stars in the bulge respond to the central mass, guiding the overall structure of the galaxy. The spiral arms of the Milky Way, the way they wind and hold together, are supported in part by the steady anchor of Sagittarius A. Without a massive centre, the galaxy would not have the same cohesion. The monster devours, but it also holds. In distant galaxies, we see the extremes of this role more clearly. Active galactic nuclei powered by feeding black holes can shut down star formation across entire galaxies, halting their growth. Jets can heat intergalactic gas, preventing it from cooling and condensing into new stars. In other cases, feedback may trigger starbursts, leading to rapid periods of stellar creation. The black hole acts as a regulator, sometimes a brake, sometimes an accelerator, but always central to the rhythm of galactic life. This dual role, destructive and creative, is part of what makes supermassive black holes so fascinating. They embody a paradox. By swallowing matter, they release energy. By consuming, they create conditions that prevent or encourage further creation. They are voids that shape fullness. Sagittarius A, though modest in its appetite today, is part of this paradox. Its past outbursts remind us that our galaxy's calm is not permanent. Its quiet influence on orbits reminds us that even in stillness it shapes. For astronomers, understanding this shaping role is more than curiosity. It is key to understanding cosmic history. The universe we see today, with its galaxies, stars and planets, was moulded in part by the feedback from black holes. Without them, galaxies might have grown unchecked, forming stars too quickly and too chaotically. With them, the growth was moderated, structured, guided. The very fact that galaxies like the Milky Way could last for billions of years, nurturing stars and planets steadily, may owe much to the presence of their central black holes. For us, lying quietly and thinking of this, it can be strange to imagine that the life we live, the breath we take, is in some indirect way connected to the influence of a monster 26,000 light-years away. Sagittarius A did not create Earth directly, but by shaping the Milky Way, by guiding its evolution, it created the conditions in which stars like the Sun could form, and planets like ours could orbit them. The destroyer is also a giver, not deliberately, not with intent, but as a natural consequence of its existence. And so, the role of black holes in shaping galaxies is not something abstract. It is part of our story. The quiet giant at the heart of the Milky Way has been working silently for billions of years, unseen and unknown until recently, yet its influence reaches even here, to the small patch of sky where we lie awake wondering about it. When people first hear about the black hole at the centre of our galaxy, the instinctive question is whether it poses a danger to us. The phrase itself, black hole, carries a certain menace, conjuring images of cosmic whirlpools sucking in everything around them. To describe Sagittarius A as a monster devouring the galaxy makes it sound as though one day it might reach out and consume Earth. But the truth, as is often the case in astronomy, is both reassuring and fascinating. The first and most important fact is distance. Sagittarius A lies 26,000 light-years away from us. That means even if it were to double or triple its appetite overnight, even if it were to flare with energy thousands of times stronger than usual, the effects here on Earth would be minimal. Light and radiation from the galactic centre reach us after travelling for tens of thousands of years, diluted across that vast distance. The black hole's gravitational pull, while immense near its horizon, weakens with distance like any other mass. At our position, the Sun's gravity dominates our orbits. The influence of Sagittarius A is indirect, shaping the galaxy's overall structure, but leaving our local system untouched. In other words, the black hole is too far away to pose a direct threat. Earth is not spiralling inward. The Sun is not being tugged dangerously. Our orbit around the Milky Way is stable, part of a cosmic carousel that takes hundreds of millions of years to complete. Sagittarius A is the hub, but we are secure on the rim. That said, there are more subtle possibilities to consider, and these are what make the question interesting. While Sagittarius A cannot swallow us directly, it can affect the galaxy in ways that ripple outward. The most dramatic involve outbursts. If the black hole suddenly consumed a large amount of matter, a gas cloud, a star, or even several stars at once, it could flare violently. Radiation in X-rays and gamma rays would stream outward, spreading across thousands of light years. At our distance, the intensity would be muted, but a sufficiently large outburst could still bathe parts of the galaxy in higher levels of cosmic rays. For Earth, shielded by its atmosphere and magnetic field, the impact would likely be small, but it could influence the upper atmosphere, potentially affecting climate or ozone levels in subtle ways. Astronomers believe such outbursts have happened before. The vast gamma-ray bubbles discovered above and below the Milky Way, stretching for tens of thousands of light years, appear to be relics of an ancient feeding episode. Sagittarius A must have been far more active a few million years ago, releasing energy on a scale that reshaped the galaxy. If humanity had existed then, we might have noticed brighter skies, unusual auroras, or changes in the cosmic ray environment. But we were not here, and now the monster sleeps more soundly. Another indirect risk involves stars wandering too close to Sagittarius A. If a star is torn apart in a tidal disruption event, the resulting flare could send waves of radiation outward. Once again, the distance protects us. The energy spreads as it travels, and by the time it reaches us it is faint. But for stars and planets closer to the galactic centre, such events can be catastrophic. Worlds near the core live under harsher conditions, bathed in radiation, tossed by crowded stellar neighbourhoods. Earth, safely tucked in the galactic suburbs, avoids that chaos. Even the jets that black holes sometimes produce pose little danger at our distance. When supermassive black holes feed heavily, they can launch narrow beams of plasma thousands of light years long, powerful enough to sterilize regions of space. If Sagittarius A ever produced such a jet, and if it happened to be pointed directly at us, the consequences could be significant. Radiation could strip atmospheres, alter climates, or even threaten life itself. But the odds are vanishingly small. Sagittarius A shows no evidence of strong jets today, and even if it did, the chance of one being aligned precisely with Earth's location is slim. It is worth remembering that space itself is full of hazards far closer to home. Supernovae, the deaths of massive stars, can release radiation bursts strong enough to affect Earth if they occur within a few dozen light years. Gamma-ray bursts, though rare, can unleash energies more intense than anything Sagittarius A could send us from 26,000 light years away. Asteroids, solar flares, and the everyday activity of our own sun present more immediate risks. By comparison, the central black hole is a sleeping giant, dangerous up close but distant enough to be almost benign from our perspective. Still, there is an allure to imagining what might happen if circumstances were different. If our solar system orbited closer to the centre, life might have had a harder time gaining a foothold. The higher density of stars would increase the chances of close encounters, disturbing planetary orbits. Radiation from Sagittarius A's activity would be more intense, potentially stripping atmospheres or sterilizing surfaces. We live where we do, in part because our galactic neighbourhood is calm. The black hole, though central, is far enough away to give us space to grow. This distance is not just luck. Galaxies form with stars distributed across vast disks, and life is more likely to arise in the quieter outer regions. Astronomers call this the Galactic habitable zone, a concept similar to the habitable zone around stars. Too close to the centre, and the risks multiply. Too far out, and there may not be enough heavy elements to build planets. Earth sits in a kind of sweet spot, far enough from Sagittarius A to be safe, close enough to the galactic centre to have the elements needed for oceans and life, There is also the question of time. Black holes evolve over billions of years. If Sagittarius A were to flare again, the effects might ripple across the Milky Way, but those timescales are immense compared to human lives. A burst that happens 1 million years from now is, for us, an abstraction. The black hole's rhythms are not our rhythms. Its meals and naps stretch across epochs, while our civilizations rise and fall in the blink of a cosmic eye. So could Sagittarius A ever threaten Earth? In the simplest sense, no. Its gravity cannot reach us. Its outbursts, while powerful, are diluted by distance. Its jets, if they existed, are unlikely to point our way. We are too far, too protected, too small in its vast arena to be in danger. And yet, in a broader sense, it has shaped us already. Its presence stabilized the Milky Way. Its feedback regulated star formation. Its quiet periods allowed life to flourish in the spiral arms. Without it, the galaxy would be different, and perhaps we would not be here to ask the question at all. The monster at the centre is not a predator stalking us. It is a force far removed, shaping the galaxy in ways both subtle and profound, but leaving our small world largely untouched. We live alongside it, not in its jaws, but under its distant influence, safe on the outskirts of its domain. Time and space are concepts we live with so constantly that we rarely question them. Seconds tick evenly on our clocks. Distances stretch in straight lines across our maps. The sun rises, the sun sets, the seasons follow their patterns, and all of it feels reliable. But near a black hole, and especially near one as massive as Sagittarius A, those familiar ideas start to unravel. What we think of as steady and universal bends and stretches in ways that defy intuition. To approach the maw of the monster is to enter a world where time itself slows, space folds in on itself, and the fabric of reality becomes something almost alien compared to the calm environment of Earth. Einstein's general theory of relativity predicted this more than a century ago. In his equations, gravity is not simply a force pulling objects together. It is the curvature of space and time caused by mass and energy. The heavier and more compact an object, the stronger the curvature it creates. Planets like Earth curve space-time only slightly. Stars curve it more. But a black hole, with millions of solar masses squeezed into a tiny region, curves it so steeply that at its event horizon, all possible paths bend inward. To understand what that means for time and space, we need to follow what happens as you approach the horizon. From the perspective of an outside observer, watching from a safe distance, time near Sagittarius A appears to slow dramatically. Imagine you could watch a clock being carried by a spacecraft descending toward the black hole. As the spacecraft draws closer, the ticks of the clock would appear slower and slower. Light leaving the clock would be stretched by gravity into redder and redder wavelengths. To you, the spacecraft would seem to crawl, then freeze, never quite crossing the horizon. But to the crew inside, their own clock would tick normally. They would cross the horizon in seconds, experiencing time as usual, even though to the outside world they seemed suspended forever at the edge. This difference is not illusion. It is the real way that time behaves in curved space-time. The closer you get, the more pronounced the effect becomes. Near the event horizon of Sagittarius A, time dilation is extreme. Hours could pass for someone falling in, while thousands of years might pass for those watching from afar. Science fiction often plays with this idea. Characters venturing near a black hole only to return and find centuries gone by. The effect is grounded in real physics. Sagittarius A, with its immense mass, is a natural time machine, stretching the flow of seconds and hours into strange asymmetries. Space itself is also distorted. Distances are no longer what they seem. Light rays bend sharply around the black hole, creating illusions where objects appear in multiple places at once. A star passing behind Sagittarius A might still be visible, its light wrapped around to reach us from several directions. space is not a backdrop but an active participant, twisting and folding under the black hole's influence. If you were near the horizon, the geometry itself would betray your expectations. Lines you thought were straight would curve, paths you thought led outward would turn inward. The more does not simply sit in space, it reshapes space itself. The experience for anything falling in would be even stranger. The tidal forces, the difference in gravity between one end of an object and the other, are lethal near stellar black holes. A person falling into such a smaller black hole would be stretched and torn apart long before reaching the horizon, a fate often called spaghettification. But Sagittarius A is so large that the gradient is gentler at the horizon. You could, in theory, cross the border intact, not noticing any sudden tearing as you entered. Only deeper inside would the tidal forces overwhelm you, pulling atoms apart, stretching molecules into nothingness. The scale of the monster changes not only the intensity, but also the timing of the destruction. For astronomers, the warping of time and space near Sagittarius A is not only a curiosity but also a tool. The orbits of the S-stars provide a way to test relativity. When the star S2 swung close in 2018, its light showed the telltale signs of gravitational redshift, stretched by the black hole's pull. The orbit itself also precesses, meaning the ellipse shifts slowly, not closing neatly like Newton's laws would predict, but rotating due to spacetime's curvature. These effects match Einstein's predictions precisely, confirming once again that relativity holds even under the most extreme conditions we can observe. Yet even with these confirmations, mysteries remain. What happens inside the horizon, at the very core of Sagittarius A? Classical relativity says there is a singularity, a point of infinite density where space and time themselves break down. But infinities are signs of incomplete theories. Many physicists believe that quantum mechanics must change the picture, smoothing out the singularity into something new. Whether that is a ball of exotic matter, a quantum fuzzball, or something entirely beyond our imagination, no one knows. The horizon hides it forever, leaving only indirect clues in the way time and space behave outside. Thinking about time near Sagittarius A also leads to paradoxes. If nothing can escape, how can black holes evaporate as Stephen Hawking suggested? Hawking radiation, a quantum effect, implies that black holes slowly lose mass, glowing faintly over unimaginable timescales. For Sagittarius A, the timescale is far longer than the current age of the universe, but in principle, even this monster will one day fade. That idea challenges our sense of permanence. Even the object that bends time so severely cannot escape time itself. From a human perspective, it is almost impossible to imagine what it would feel like. We live in a world where time flows evenly, where distances are steady, where light moves in straight lines. To think of time slowing, of space curving, of light looping back on itself is to step into a reality so different that it feels like fantasy. And yet, it is not fantasy. It is the real behaviour of the universe near Sagittarius A. Our instruments confirm it, our equations describe it, and the stars themselves testify to it in their orbits. Time feels so relentless in everyday life, always slipping away, always hurrying us forward. But near the maw of the monster, time itself is not absolute. It bends, it stretches, it slows. The universe is not as rigid as it seems. Even the ticking of seconds is negotiable, depending on where you are and how strong the gravity is. That thought can make our own worries about time feel smaller, just another local rhythm in a cosmos where clocks are never universal. Imagining what it would feel like to fall into Sagittarius A is both unsettling and strangely captivating. It is the kind of thought experiment that lies at the border between physics and imagination, where equations describe the forces but the mind supplies the experience. For most of us, black holes exist only as distant abstractions, numbers written in textbooks or images blurred into glowing rings. But to place yourself, even in thought, on a trajectory inward toward the maw of the monster is to glimpse a reality that is as awe-inspiring as it is terrifying. The journey would begin long before you reach the event horizon. As your spacecraft approached the galactic centre, the stars would grow denser. Near the core, the night sky would look radically different from the one you know. Instead of a scattering of faint points, it would be crowded with thousands of bright stars, so many that the sky would seem ablaze. The closer you came, the more those stars would streak and blur under the influence of gravity, their light bent and distorted. Already the strangeness of space-time near Sagittarius A would be visible. As you drew nearer, the black hole itself would begin to dominate the view. You would see not a hole but a sphere of darkness surrounded by a halo of glowing gas. Light from the accretion disk would curve around it, allowing you to see both the near and far sides of the disk simultaneously. The shadow at the centre would look impossibly sharp, an absence of stars where your instincts would expect brightness. The sight alone would be disorienting, a reminder that you were leaving the familiar universe behind. If you continued inward, tidal forces would start to make themselves felt. Gravity pulls more strongly on whatever is closer to the black hole, and less strongly on whatever is farther. For small black holes, this difference becomes lethal far outside the horizon, stretching objects into long, thin strands. This process, called spaghettification, turns any infalling matter into noodles of plasma before it ever crosses the event horizon. But Sagittarius A is supermassive, and at its horizon, the gradient of gravity is gentle enough that you could, in theory, cross it intact. The stretching would not overwhelm you instantly. You might not even feel it at first. That is one of the paradoxes of supermassive black holes. They are both gentler and more dangerous depending on how far you go. From the perspective of someone watching your fall from a distance, the scene would unfold differently. To them, your descent would appear to slow as you neared the horizon. The light from your ship would stretch into redder wavelengths, fading into invisibility. You would seem to freeze at the edge, never quite crossing. But from your point of view, time would feel normal. You would plunge forward, and the horizon would pass without ceremony. One moment you would be outside, the next inside with no visible barrier. The difference between perception and reality is one of the most disorienting aspects of falling in. Inside the horizon, all paths lead inward. No maneuver, no thrust of engines, no beam of light could turn you back. Space-time itself tilts toward the singularity, and your future is bound to it. The tidal forces would continue to grow, slowly at first, then rapidly. Molecules would stretch, atoms would be torn apart. You would be elongated into a thread of matter, thinner and thinner, until your very particles were scattered. In the language of physics, your world line, the path you trace through space-time, would end at the singularity. In human terms, you would be reduced to nothing. It is unsettling, but it is also remarkable that physics can describe this so clearly. The equations of general relativity map out the curvature of space-time, the trajectory of your fall, the fate of your body. They tell us where time slows, how light bends, when spaghettification begins. They give us the rules of a place we cannot visit, a place no traveller can return from. To fall into Sagittarius A is to enact those equations to become part of the very structure Einstein described. And yet, there are mysteries that equations cannot resolve. What exactly happens at the singularity is unknown. Relativity predicts infinite density, but infinities are signs of incomplete understanding. Quantum mechanics, with its rules for the very small, must come into play, but we do not yet know how. Some theorists imagine the singularity is replaced by a ball of exotic quantum matter. Others suggest that space-time might fold into another region of the universe, or even another universe entirely. To fall into Sagittarius A is to cross into this unknown, to leave behind not only the familiar universe, but the reach of current physics. From a more personal perspective, the fall would also bring disorientation of time. Near the horizon, your clock would tick normally, but outside, the universe would appear to accelerate. Stars would whirl faster, galaxies would age, the cosmos itself would race ahead. If you could somehow look back outward during your descent, you might watch billions of years unfold in what felt like moments. The outside universe would rush into the future while you fell toward your own inevitable end. In that sense, falling into Sagittarius A is not only a journey into space but also into time, a shortcut into the far future of the cosmos. Of course, this is a thought experiment. No spacecraft, no astronaut will ever make this journey. The radiation near the accretion disk, the heat of the plasma, the sheer difficulty of reaching the galactic centre make it impossible. But by imagining it, by following the rules of physics into the more, we gain perspective on what black holes really are. They're not just metaphors of destruction. They are places where the familiar fabric of reality breaks, where the ordinary concepts of distance and time dissolve. To fall into one is to confront the limits of human understanding. The image of being stretched into nothingness might seem frightening at first, but it also puts into perspective how small and brief our everyday concerns are. Against the scale of a supermassive black hole, even spaghettification becomes part of the vast order of nature, no more or less dramatic than the life of a star or the orbit of a planet. It is a reminder that the universe is immense and we are fragile, but fragility does not make us unimportant. It makes our moments precious. To think of a black hole is to think of an ending. It is the place where stars disappear, where matter is swallowed, where time and light themselves find no escape. And yet, when astronomers study black holes, they find something paradoxical. In the very act of destruction, black holes create. They release energy, stir gas, sculpt galaxies, and even make possible the birth of new stars. Sagittarius A, the monster at the heart of our galaxy, is not only a devourer, but also a hidden architect. This paradox, creation born from annihilation, sits at the heart of understanding what black holes truly mean in the universe. The process begins with feeding. Matter spiraling towards Sagittarius A is heated, ionized, and accelerated to near-light speeds. Most of that matter will eventually vanish beyond the event horizon, but before it does, it radiates. That radiation carries energy outward, heating nearby gas clouds, stirring turbulence, and triggering shock waves. Paradoxically, the act of swallowing creates a blaze that illuminates. Even in its current quiet state, Sagittarius A sometimes flares in bursts of X-rays and infrared light. In more active phases, as we suspect it had millions of years ago, it would have glowed as brilliantly as a quasar, outshining the combined light of billions of stars. Those outbursts shape the galaxy, carving bubbles, compressing gas, and altering where stars are born. On cosmic scales, this feedback is essential. Without it, galaxies might collapse their gas into stars too quickly, exhausting their fuel early in cosmic history. Instead, black holes regulate the process. They blow some gas away, slowing star formation, but they also compress gas clouds, sometimes sparking new bursts of stellar birth. This dual role makes them both destroyers and midwives. The monster devours, and in devouring, it ensures the galaxy's future. We see the evidence across the universe. In distant galaxies, jets from black holes stretch for thousands of light years, injecting energy into intergalactic space. These jets prevent gas from cooling too rapidly, balancing the pace of star formation. In our own Milky Way, the Fermi bubbles, vast structures of gamma rays above and below the galactic plane, are thought to be relics of past activity from Sagittarius A. They testify that our black hole once unleashed enough power to reshape the galaxy, on scales we can still trace today. What was destruction then, consuming stars or gas clouds, has left behind creation in the form of structure and balance. Even on smaller scales, the paradox is clear. When a star wanders too close and is torn apart, half of its material may be flung outward instead of swallowed. That expelled matter can enrich the galactic environment with heavier elements, seeding clouds that may later form planets. A death near Sagittarius A becomes part of the cycle of life elsewhere. In that sense, even annihilation contributes to creation. This paradox extends to the level of physics itself. Black holes are places where energy conversion reaches its peak efficiency. Matter falling in can release up to 10% of its mass as energy, far higher than nuclear fusion, the process that powers stars. That energy is not lost to the universe. It floods outward, shaping environments, influencing galaxies, and sometimes even reaching intergalactic voids. A place that seems to erase becomes a source of radiance. It is tempting to think of this in human terms as a kind of redemption, as though destruction justifies itself by leading to creation. But the reality is more neutral, more natural. Black holes are neither good nor evil. They do not intend to destroy or to create. They simply follow the laws of physics. In doing so, they become the engines of paradox, shaping galaxies through the very acts that erase stars. For Earth, this paradox is personal. Our Sun, our planets, our very existence depend on the long history of star formation in the Milky Way. That history was moderated by Sagittarius A. If the galaxy had formed stars too quickly, it might have burned out long before the Sun appeared. If it had formed too few, the heavy elements needed for planets and life might never have accumulated. By regulating the galaxy, by balancing destruction with creation, Sagittarius A helped set the stage for us. Without the monster, there might have been no humans to lie awake pondering it. There is another level to the paradox. The more matter Sagittarius A consumes, the more powerful it can become, yet the more it feeds, the more it radiates outward, resisting further feeding. This feedback loop keeps black holes from growing unchecked, stabilizing their galaxies. Destruction limits itself, and creation emerges from the balance. The monster shapes its own boundaries. Even the concept of Hawking radiation fits this paradox. Though it is a quantum effect and faint beyond measurement for supermassive black holes, it suggests that in the very long run, even black holes evaporate. Their destruction is not eternal. They return energy to the universe, particle by particle, until nothing remains. The ultimate erasers eventually erase themselves, and in doing so, give back what they took. Creation lies even in their end. For astronomers, studying this paradox is not simply philosophy. It is essential to understanding cosmic history. The universe we see today, galaxies full of stars, planets with oceans, worlds that might harbour life, was shaped by the balance between black hole destruction and black hole creation. The cycle of consumption and feedback, of swallowing and radiating is written into the structure of the cosmos. Sagittarius A is part of that cycle, one thread in a vast tapestry that links annihilation to Genesis. This paradox may bring a kind of peace. We tend to think of endings as final, of destruction as loss, but in the universe, even destruction is folded into creation. The star that is torn apart enriches the gas that forms new stars. The gas that is swallowed sparks radiation that sculpts galaxies. The black hole that devours ultimately gives back through its influence. The monster is not only an end, but also a beginning. For all we have learned about Sagittarius A, for all the orbits we have mapped, the flares we have recorded, and the images we have pieced together from across the Earth, there remains an ocean of uncertainty. The black hole at the centre of the Milky Way is a paradoxical combination of familiarity and mystery. It is the closest supermassive black hole we know, the one we can study with the greatest detail, and yet it still hides its most important secrets behind an event horizon that no signal can cross. To acknowledge what we still do not understand is not a sign of failure, but a reminder that discovery is never finished, that every answer opens new questions, and that even the most carefully measured object in the galaxy still leaves us wondering. One of the most pressing questions concerns the singularity itself. According to Einstein's equations, all the mass of a black hole is compressed into a single point of infinite density at the centre. But infinities in physics are red flags, markers that a theory has been pushed beyond its range. What really lies inside Sagittarius A is still unknown. Some physicists imagine that quantum mechanics softens the singularity into something finite, a dense but not infinite core. Others suggest that space and time themselves may be quantized, broken into tiny grains that prevent infinite collapse. Without a complete theory of quantum gravity, we cannot say. The horizon hides whatever is truly at the heart of the monster. Another open question is how Sagittarius A formed. We know that stellar black holes are created when massive stars collapse, but supermassive black holes are another matter. No single star is large enough to collapse into 4 million solar masses. Did Sagittarius A begin as a smaller black hole that slowly grew by consuming gas and stars? Did it form from the direct collapse of an enormous gas cloud in the early universe? Or did multiple black holes merge together during the galaxy's youth? Each possibility carries different implications for how galaxies themselves evolve. The history of Sagittarius A is written in its mass, but the script is still unclear. There is also the puzzle of its feeding habits. Why is Sagittarius A so quiet today, compared to the blazing quasars in other galaxies? Is it simply a matter of fuel, that little gas and dust now reach the centre? Or is there something about the dynamics of the Milky Way that prevents steady feeding? The occasional flares we see suggest that matter does fall in, but the process is sporadic, irregular, almost hesitant. Understanding why Sagittarius A is underfed may reveal not only its present state, but also its future. Could it flare again, as it seems to have millions of years ago, or will it remain dormant for eons to come? The jets, too, remain mysterious. In some black holes they stretch for thousands of light years, blasting matter into intergalactic space. In Sagittarius A they seem absent, or at least faint. Why? Is it because the black hole is currently starved, or because the orientation of its magnetic field suppresses jets? Could hidden, weak jets be escaping in ways we have not yet detected? The physics of jet formation is still one of the great unsolved problems of astrophysics, and Sagittarius A offers an important but puzzling case study. Even the orbits of stars raise questions. The S-stars have provided proof of the black hole's mass, but their very existence near the centre is odd. These stars are young, massive and hot, yet the tidal forces near a supermassive black hole should make star formation difficult. How did they come to be there? Were they born farther out and migrated inward, or is there some mechanism we do not yet understand that allows stars to form in the harshest gravitational fields? The S-stars testify to mysteries of stellar dynamics in extreme environments. And then there is the problem of information. According to classical physics, anything that falls into Sagittarius A is lost forever, its details erased from the universe. But quantum theory insists that information cannot be destroyed. Stephen Hawking's work on black hole evaporation sharpened this paradox. If black holes radiate over time, then what happens to the information about what fell in? Is it encoded in subtle correlations in the radiation? Is it smeared across the event horizon itself, as the holographic principle suggests? Or is information truly lost, forcing us to revise the foundations of physics? The information paradox is not an abstract puzzle. It is a question that lies at the heart of Sagittarius A, waiting for a resolution. There are also practical uncertainties. Even with the Event Horizon Telescope, our images of Sagittarius A are blurred. The hot gas moves too quickly, changing from moment to moment, making it difficult to capture a steady picture. Future instruments may sharpen the view, perhaps even show the disk in motion, but for now we see only outlines and approximations. What details lie hidden in that blur? Could subtle deviations reveal new physics, cracks in relativity, hints of quantum gravity. The image we have is extraordinary, but it is also only the beginning. And beyond these questions lies the largest uncertainty of all: how black holes fit into the ultimate fate of the universe. Will Sagittarius A and others like it continue to grow, swallowing stars until galaxies fade away? Will they eventually evaporate through Hawking radiation, leaving nothing behind? Will new physics reveal some other destiny? Our galaxy's black hole is not just a local feature. It is part of the cosmic story, and its fate is tied to the fate of everything. The fact that Sagittarius A still resists our full understanding is not a failure but a gift. It means there is more to discover, more to wonder at, more questions to ask. The monster at the centre is not just an answer, but a source of endless inquiry. To live in the Milky Way is to live in the presence of something enormous and hidden. Most nights, when you look up at the sky, you see stars scattered across the darkness, some familiar, some faint, some clustered into the pale band we call the galactic plane. You may not think of what lies at the centre, because it is invisible, quiet, and unimaginably far away. Yet there it is, Sagittarius A, the supermassive black hole, whose gravity holds the galaxy together, whose past outbursts have shaped its structure, whose very existence makes our home what it is. We live our entire lives in its domain, orbiting around it without ever noticing, like dancers tracing patterns in a music too low for us to hear. There is something humbling in this. Black holes are often described as monsters, destroyers, devourers of worlds, and yet Sagittarius A is also a guardian of sorts, keeping the stars of the Milky Way bound together. Without it, the galaxy might not have the structure we see. Without its regulating influence, stars might have formed too quickly or too slowly. It is both danger and necessity, both abyss and foundation. To sleep at night knowing it is, there is to accept that the universe is full of contradictions, and that sometimes the very things we fear are also the things that make us possible. What makes this reflection soothing is the distance. At 26,000 light-years away, Sagittarius A is no threat to us. It is too far, too restrained, too quiet. Its flares cannot scorch us. Its gravity cannot reach us. We live in the safe suburbs of the galaxy, far from the chaos of the core. We can study the monster without being consumed by it. We can learn from its whispers, its shadows, its flares, and its influence. But we are not in its jaws. For all its power, Sagittarius A is a silent companion, not a predator, a presence woven into our lives without ever intruding. Lying here, it is strange to think that everything we know, every person, every memory, every sound, every story, exists inside a galaxy that turns slowly around this invisible heart. The Earth itself drifts in a path shaped by Sagittarius A's gravity, circling in a cosmic orbit that takes hundreds of millions of years to complete. Civilizations rise and fall in moments compared to that journey. Species appear and vanish in the blink of a galactic eye. The black hole remains, patient, timeless, steady. It will be there long after we're gone. It was there long before we began. And perhaps that is part of why the thought is comforting. Against the rush of daily time, against the urgency of human worries, Sagittarius A is slow and constant. Its rhythms are measured in millions of years. Its changes unfold across epochs. It does not hurry. It does not rush. It waits in silence, shaping without demanding, existing without judgment. To rest under its influence is to remember that not all time is short, not all scales are human. There is peace in the vastness, in knowing that our lives are small but not meaningless, part of a structure larger than we can see. The black hole is invisible, but we have made it visible in our minds. We have listened to its radio whispers. We have watched stars circle it in strange and elegant orbits. We have captured the glow of its accretion disk and pieced together the shadow of its horizon. With tools and patience, we have turned the unseen into knowledge. We cannot cross its boundary, but we can trace its outline. We cannot know what lies inside, but we can learn from everything around it. To sleep beside a cosmic giant is also to live with curiosity, to ask questions that may never be fully answered, and to find joy in the asking. For many people, the image of Sagittarius A released by the Event Horizon Telescope was a kind of revelation. A blurry ring of light around a dark centre, simple at first glance, but profound in meaning. It was a confirmation that the invisible is real, that the monster at the heart of the galaxy is not a myth but a fact, that our understanding of the universe can reach even into places where light itself cannot escape. That ring is now part of human culture, a symbol of both our fragility and our strength, our limits and our reach. And so tonight, as you lie here, perhaps you can picture that ring, not as something frightening, but as something steady. A reminder that the galaxy has a heart, that even in darkness there is light, and that we are connected to it by the very fact of being here. The atoms in your body, forged in the cores of stars, circle the galactic centre, along with every other star, planet and cloud. You are part of the Milky Way, part of the orbit around Sagittarius A, part of the dance that has gone on for billions of years. To sleep beside a cosmic giant is to accept that we are small, but also that small things can know big truths. The monster does not notice us, but we notice it. The abyss is silent, but we have given it a voice. The event horizon hides everything beyond it, but we have traced its outline. In that balance, there is comfort. We cannot change the giant, but we can live with it, learn from it, and dream in its shadow. And as your eyes grow heavy, as your thoughts drift, you may find that thinking of Sagittarius A is not frightening at all. It is distant, quiet, patient, and in its silence it invites you to rest. It has been there for billions of years, and it will remain for billions more. Tonight it waits, as it always does, at the centre of the galaxy, a reminder that even in the vastness of space we are never alone. And so, as we let our thoughts drift outward once more, away from the centre of the galaxy and back toward the quiet of our own night sky, we return to stillness. The monster at the heart of the Milky Way continues its patient watch, unchanged, unhurried, unseen. Here on Earth, the air is steady, the stars above are familiar, and the only pull you feel is the gentle rhythm of your own breathing. If you found this time together soothing, you're always welcome to return, to drift again into science and story, into calm wonder at the universe. You can join this space by liking, subscribing, or simply coming back whenever you need company beneath the stars. Now, as the night deepens, let the vastness fade into the background. Let your body soften into rest, and let your mind settle in the comfort of knowing that you are safe, small, and part of something immeasurably large. Sleep well, and until next time, good night.